There is a galaxy out there that defies expectations. Not because it's the biggest, or the brightest, or the closest, but because it erupts with death more often than almost any other. Its name is NGC 2770, and on the surface, it looks like a typical spiral galaxy, peaceful, elegant, quietly rotating through the cosmos. But hidden behind its calm appearance is a violent truth. In just 10 years, this galaxy gave birth to 3 spectacular type IB Supernovi, massive stellar explosions so powerful, they release more energy in a few days than our Sun will emit in its entire lifetime. But before we continue, subscribe to the channel so you don't miss out on any of these videos. Astronomers call NGC 2770 the Supernova Factory. It's not just a nickname, it's a warning. Supernovae are rare events, especially of the same type, in the same galaxy, occurring so close together in time. For a single galaxy to host 3 type IB supernovae within a single decade is not only exceptional, it challenges our understanding of how stars live and die on a galactic scale. This galaxy isn't famous for its size or for hosting a supermassive black hole like some of the more well-known cosmic giants. NGC 2770's notoriety comes from a different kind of spectacle, the sudden and violent deaths of massive stars. These deaths aren't quiet. They're loud, they're bright, and they ripple across the fabric of space and time. But how did we come to know this galaxy? What makes it so special? Why are its stars dying in such rapid succession, and what secrets might this place hold for the future of supernova research? In this video, we'll take a journey deep into the life of NGC 2770, a spiral galaxy tucked away in the night sky, yet screaming with light every few years. We'll look at the supernovae themselves, the rare conditions that make them possible, and the groundbreaking discoveries that happened entirely by accident. Along the way, we'll explore the structure of galaxies, the life cycles of massive stars, and the extraordinary instruments used to capture these brief but monumental events. NGC 2770 may not be the most famous galaxy in the sky, but in the world of astrophysics, it has become one of the most unforgettable. Because in the darkness of space, NGC 2770 doesn't just twinkle, it explodes. To find NGC 2770, you wouldn't look toward the dazzling constellations that dominate stargazing books or amateur telescopes. You'd turn your eyes towards something far less famous, Lynx. Nestled between the more recognizable constellations of Ursa Major and Gemini, Lynx is a faint and often overlooked stretch of sky, devoid of bright stars. In fact, it was only officially catalogued in the 17th century, specifically because early astronomers needed something to fill the blank space between other constellations. It's quiet, sparse, and unimposing, much like NGC 2770 itself appears at first glance. But within this subtle constellation, about 88 million light-years away from Earth, lies a spiral galaxy that's anything but quiet. When we speak of distance in astronomy, it's easy to become numb to the scale. 1 million light-years? That's already beyond comprehension. But 88 million? That's 88 million years for the light from this galaxy to reach us. Every time we look at NGC 2770, we're not seeing it as it is now, we're seeing it as it was 88 million years ago. Back when dinosaurs still ruled the Earth, the photons that now touch our telescopes began their journey from a star system we now know to have gone supernova. In a sense, this galaxy has been whispering its story to us across the ages, and we're only just beginning to listen. Because it's so far away and located in a rather dim section of the sky, NGC 2770 isn't visible to the naked eye. You won't spot it in backyard telescopes unless you're using more advanced equipment under very dark skies. But professional observatories and space-based instruments have captured it in exquisite detail. Its spiral arms, its structure, and, most importantly, its explosive secrets have become the focus of intense astronomical scrutiny. The galaxy is also slightly inclined when viewed from Earth, giving us a partial edge on perspective. This angle lets astronomers study its disk and arms more effectively than if we were staring directly face-on. And through this view, we've caught glimpses of the regions where stars are being born, and where others are dying. What makes its location even more ironic is how unassuming Lynx is. In a sky full of legendary beasts, Leo the lion, Draco the dragon, Pegasus the winged horse, Lynx is a creature known for its quiet, stealthy nature. Yet hiding within it is one of the most volatile and active supernova-producing galaxies we've yet discovered. It's as if the universe decided to play a game of cosmic contrast, burying a violent jewel inside a forgotten constellation. As telescopes sweep across this region of the sky, data continues to pour in, not only from NGC 2770, but from the faint galaxies surrounding it. Yet none have told a tale quite as compelling, nor erupted in such fiery fashion, as the Supernova Factory, hidden in Lynx. To understand the strange behavior of NGC 2770, we need to understand the type of stellar explosion it keeps producing, type IB Supernovi. These are not your average cosmic fireworks. They are part of a rare class of supernovae, distinct from the more commonly known type II or type I, and they come with their own set of clues about the lives and deaths of stars. At the heart of every type IB supernova is a massive star, far larger than our Sun. These stars are true giants, often 10 to 25 times the Sun's mass, burning hot and bright and living fast lives. But what makes a type IB so unique is what it doesn't have: a hydrogen envelope. Normally, massive stars are surrounded by thick outer layers of hydrogen, the most abundant element in the universe and the primary fuel for stellar fusion. But in a type IB supernova, that hydrogen has already been stripped away by the time the star dies. This missing layer gives astronomers a critical clue. When these stars explode, they leave behind a light signature that lacks the telltale hydrogen emission lines found in other supernova types. Instead, the spectrum of a type IB is rich in helium, meaning the star's outer layers were removed, either by fierce stellar winds or by interactions with a binary companion that literally siphoned the hydrogen away over time. That detail changes everything. It means that type IB supernovae are not only violent, they're personal. They tell us something specific about the life history of the star, that it likely existed in a more complicated stellar environment, with forces strong enough to peel away its outer layers. These are stars that lived in neighborhoods of intense radiation, gravitational struggle, and rapid evolution. Once the hydrogen is gone, the star burns through helium and heavier elements until it can no longer hold back the force of its own gravity. At that point, the core collapses catastrophically. In a fraction of a second, the core turns into either a neutron star or a black hole, and the outer layers are blasted into space in an explosion that can briefly outshine an entire galaxy. Type IB supernovae are part of a broader family called stripped envelope supernovae, which also includes type IC, where even the helium is gone. They're rare, accounting for only a small fraction of all observed supernovae. That rarity is part of what makes NGC 2770 so intriguing. It hasn't just produced any supernovae, it has produced 3 type IB supernovae in a row, as if its stars are being built from a specific mold, massive, short-lived, and already halfway stripped before they even die. These explosions are more than just flashes in the sky. They're laboratories of physics. Within their shockwaves, temperatures and pressures rise to levels that cannot be replicated anywhere else. They forge elements like calcium, oxygen, and even some of the iron in your blood. Type IB supernovae, like all core collapse events, are part of the universe's grand cycle of creation through destruction. So when NGC 2770 erupted not once, not twice, but 3 times with this specific type of supernova, astronomers took notice. It wasn't just a fluke, it was a message. Something in that galaxy is creating the perfect conditions to build and destroy stars in exactly this way. And the deeper we look into these explosions, the more we begin to understand the complex, layered lives of the stars that light our universe. The story of NGC 2770's violent reputation begins not with fame, but with quiet observation. Before it was dubbed the Supernova Factory, before its name circled through research papers and observatory logs across the world, it was just another spiral galaxy catalogued among the countless others. That all changed in late 1999, when a star in NGC 2770 died, and not just any star, but a massive one, stripped of its outer hydrogen shell, collapsing under its own weight in a cosmic exhalation of light and energy. This explosion would later be named SN2008D, the first of 3 known type IB supernovae recorded in the galaxy. It was the spark that lit the fuse, drawing NGC 2770 out from obscurity and into the sharp focus of the astronomical community. On November 8, 1999, observers at the Lick Observatory in California were conducting a routine scan as part of the Katzmann Automatic Imaging Telescope (KIT) Supernova Search program. This telescope was designed for automatic sky monitoring, capable of taking nightly images of nearby galaxies to detect sudden changes, such as a supernova lighting up in one of its arms. And that night, it delivered. The data returned showed something new, an object that wasn't there before. A bright point of light, unlisted in star catalogs, had appeared near the edge of one of NGC 2770's spiral arms. Over the following nights, it grew in brightness, confirming it was not a simple anomaly or asteroid reflection. This was a stellar explosion in progress. The new light source was officially designated SN2008D. Follow-up spectroscopic studies soon revealed its nature, a type IB supernova. The spectrum showed no signs of hydrogen, but strong helium lines, telling astronomers that the exploding star had lost its outer hydrogen layer before collapse. At the time, this wasn't necessarily a shocking event. Type IB supernovae had been observed before. But even then, they were rare, and most occurred in galaxies with extremely active star-forming regions. NGC 2770 did not initially seem like one of them. SN2008D peaked at a magnitude of around 16.5 in visible light, too faint for the naked eye, but well within the grasp of modern telescopes. Over the days and weeks that followed, astronomers tracked its light curve, measuring how it brightened and then slowly faded. The shape of that light curve is critical. It's one of the fingerprints of a supernova. For SN2008D, the curve was consistent with expectations for a type IB, a sharp rise followed by a gradual, radioactive-powered decline. At the core of the supernova's explosion, radioactive nickel-56 was forged in enormous quantities, and its decay into cobalt-56, and eventually iron-56, powered the fading afterglow. This radioactive decay acts like a cosmic light bulb, keeping the remnants visible for weeks or months. The estimated progenitor of SN2008D was likely a massive star with an initial mass around 15 to 25 times that of our Sun. While direct imaging of the progenitor star was not possible due to the galaxy's distance and lack of pre-explosion deep-field imagery, modeling based on the light curve and spectral features suggested it was a Wolf-Rayet star, a type of star known for shedding its hydrogen envelope through powerful stellar winds. Wolf-Rayet stars are rare and short-lived, often considered ticking time bombs in stellar evolution. Their loss of mass exposes their hot, inner layers, allowing elements like helium, carbon, and oxygen to dominate their spectra. These stars are expected to end their lives in core collapse supernovae, making them strong candidates for type IB and IC progenitors. If SN2008D did indeed originate from such a star, it would have been one of the galaxy's most massive and luminous residents, now gone in an instant, but leaving behind a fireball that stretched across interstellar space. But what caught astronomers' attention most wasn't just the nature of the supernova, but where it happened. The explosion occurred in a relatively modest star-forming region within NGC 2770. Unlike galaxies undergoing frenzied starburst activity, like M82 or ERP 220, NGC 2770 seemed, at the time, almost ordinary. Its spiral arms were moderately defined, its core not unusually active, and its overall star formation rate relatively close to that of the Milky Way. Yet here was a textbook type IB event, an explosion typically associated with the kind of massive stars that form rapidly and die young. This led to questions. Was this just a coincidence? A one-off event? Or had astronomers simply been overlooking galaxies like NGC 2770 for too long? At the time, there were no answers. SN2008D faded from view as all supernovae eventually do, and the galaxy once again faded into the backdrop of the sky. But the seed had been planted. NGC 2770 was now a marked target, one that had produced a rare type of supernova. It would remain on the watch lists of observatories around the world. Telescopes would continue to check in, scan its arms, and log its emissions. Years would pass, and nothing would seem out of the ordinary. Until it happened again. And this time, it would come with a twist no one saw coming. 8 years after the quiet spectacle of SN2008D, astronomers turned their gaze once more to NGC 2770, perhaps out of routine, perhaps out of intuition. What they found was that the galaxy had stirred again. In late December of 2007, a second supernova began to bloom in one of its spiral arms. It was as if the galaxy, once thought to be ordinary, had flared up once again with another cosmic death. This time, the event was brighter, more energetic, and caught the attention of astronomers far more rapidly. The explosion was named SN2008, and it confirmed what the first supernova had only hinted at: NGC 2770 was not done erupting. The discovery came on December 31, 2007. Using the Catalina Real-Time Transit Survey and several other sky monitoring networks, astronomers spotted a bright, new object in the southern region of NGC 2770's disk. Almost immediately, it was recognized as a supernova, and the data pointed again to something familiar: another type IB. This event was different from SN2008 in more ways than just brightness. SN2008 exhibited a remarkably fast rise in luminosity, reaching an apparent magnitude of approximately 15.3, making it noticeably brighter than its predecessor. For a galaxy nearly 88 million light-years away, that's no small feat. The explosion was powerful enough to be picked up by multiple observatories worldwide, including ground-based telescopes in both hemispheres. Almost instantly, spectroscopic follow-ups confirmed the presence of helium lines and the absence of hydrogen, marking it, once again, as a type IB. By this point, astronomers were not just interested, they were intrigued. 2 type IB supernovae in the same galaxy within a span of a few years? Statistically rare? But it wasn't just the recurrence that made SN2008 important, it was the depth of the data collected. Telescopes across the electromagnetic spectrum turned toward NGC 2770. Optical light, radio waves, ultraviolet observations, everything was mobilized. This wasn't just about recording another explosion. It was about understanding the environment of the host galaxy, the characteristics of the progenitor star, and the overall behavior of NGC 2770 as a whole. The light curve of SN2008 was well tracked and well defined. It showed a fast rise to maximum brightness, followed by a steady decline consistent with the radioactive decay of nickel-56 and cobalt-56, just as seen in SN2008. But there were nuances. The spectral lines were broader, suggesting faster-moving ejecta. The presence of asymmetry in the velocity profiles hinted at a more complex internal explosion, perhaps a core collapse that wasn't perfectly spherical, or even the presence of jets, although those remained speculative. There was also the question of progenitors. Like with most extragalactic supernovae, the exact star that exploded was not directly observed before the blast. But once again, models pointed toward a massive Wolf-Rayet star, those luminous, hot stars known for powerful winds that strip away their hydrogen. These stars are already well on their way towards stellar death long before collapse, and when they go, they do so with violence befitting their short and furious lives. One of the more compelling elements of SN2008 was the potential for it to serve as a beacon, an astronomical, bat signal, to tell scientists something was brewing in NGC 2770. But what came next would outshine even the second flash. Because even as the data from SN2008 was being analyzed, something unexpected occurred, just 10 days later. On January 9, 2008, all telescopes were still fixed on NGC 2770 from the recent supernova. Another explosion erupted. This one would not be seen first in visible light, but in high-energy X-rays. It was an accidental discovery, completely unplanned, completely serendipitous. And it would change everything. SN2007 though striking in its own right, now served as the middle chapter in a trilogy of cosmic events that would transform NGC 2770 into something extraordinary. Its timing, just days before the third explosion, meant that multiple telescopes were already monitoring the galaxy in unprecedented detail, giving scientists one of the most comprehensive observational datasets surrounding any supernova to date. And in the background, NGC 2770 continued to rotate silently, calmly, hiding the chaos churning beneath its surface, waiting to release yet another star's death cry into the void. On January 9, 2008, just as astronomers were busy monitoring the fading brilliance of SN2007 NGC 2770 unleashed yet another explosion. But this time, the universe let us witness something that had never been captured before. It wasn't the light of the supernova itself that was seen first. It wasn't even detected through the traditional optical surveys that usually signal such discoveries. Instead, the first signal came in the form of a sharp burst of X-rays, high-energy radiation emitted in the opening seconds of a star's death. This unprecedented event marked the discovery of SN2008D, and it happened entirely by accident. NASA's SWIFT satellite, a space-based observatory designed primarily to study gamma-ray bursts, GRBs, was pointed at NGC 2770, but not because astronomers were expecting a supernova. In fact, SWIFT was observing the galaxy for calibration purposes. The target at the time was not a dying star, but simply the lingering afterglow of SN2007 the supernova that had occurred just days before. But during this routine observation, something extraordinary happened. SWIFT's X-ray telescope, XRT, detected an intense, short-lived flash of X-rays coming from a completely different region of the galaxy. The signal lasted only about 600 seconds, 10 minutes, and then it faded. This alone was unusual. Most X-ray bursts associated with gamma-ray bursts are either much shorter or connected to completely different physical processes. The SWIFT team initially suspected it had caught a low-luminosity gamma-ray burst, but follow-up observations quickly revealed something else. The X-ray flash wasn't a separate event, it was the very beginning of a supernova. For the first time in human history, astronomers had caught a supernova in the act of exploding, right at the precise moment when the shockwave from the collapsing star punched through the outer layers of the star and released a flood of X-rays into space. This moment, called the shock breakout, had long been theorized but never directly observed. It's the very instant when the explosion breaches the surface of the star and releases an intense, sudden burst of radiation. Normally, by the time the supernova becomes visible in optical light, hours or even days have passed since the actual moment of detonation. But SN2008D was different. We saw its birth, not just its aftermath. Immediately after the X-ray flash, ground-based observatories jumped into action. Optical follow-up observations began within minutes. What started as a mysterious X-ray signal soon grew brighter in visible light, confirming that a new supernova had erupted, one that hadn't yet been catalogued. And just like its two predecessors, the spectrum showed the distinctive fingerprints of a type IB, helium lines, no hydrogen, and broad absorption features indicating rapidly expanding material. This wasn't just a discovery, it was a milestone in astrophysics. For decades, supernovae had been studied after the fact, their light curves and spectra telling stories long after the initial drama had passed. But with SN2008D, the universe had handed scientists the keys to the front door. We weren't just spectators to the aftermath anymore, we were eyewitnesses to the ignition. From the shock breakout onward, every moment of SN2008D was studied with unprecedented detail. Observatories all over the globe joined in, the Very Large Telescope in Chile, the Keck Observatory in Hawaii, the Gemini telescopes, and even Hubble. They watched as the optical light brightened and faded, as the spectrum evolved, as the blast wave cooled and expanded. But the X-ray data from SWIFT remained the crown jewel. It told a story in seconds that optical light couldn't tell in hours. The initial X-ray burst confirmed that the progenitor was a massive star, likely a Wolf-Rayet, collapsing directly into a compact object, either a neutron star or a black hole. The X-rays revealed the energy and timing of the explosion in ways never before possible, providing direct evidence of the shockwave theory that had, until then, only existed in simulations and indirect modeling. This also had enormous implications for supernova detection going forward. If more observatories could monitor galaxies in X-rays, we might be able to catch other supernovae the instant they ignite, unlocking new data about their progenitors, their environments, and the physics of stellar collapse. It became clear that optical telescopes, while powerful, had been missing the first few pages of the story. X-rays, fleeting and hard to catch, were the opening lines. As SN2008D continued to unfold, astronomers marveled not only at its nature but at the stunning timing of its discovery. If SN2007 had not exploded just days earlier, Swift would not have been pointed at NGC 2770. And if Swift hadn't been observing that part of the galaxy at precisely that time, the X-ray flash would have been missed entirely. The window was minutes long, a narrow cosmic blink, and we caught it. It's hard to overstate how rare this is. Supernovae, as explosive as they are deeply unpredictable. Astronomers can identify star-forming regions and estimate likely candidates, but they can't predict exactly when or where one will erupt. To have a telescope pointed at the right galaxy, at the exact moment of core collapse, is like trying to photograph a lightning bolt without knowing there's a storm. It was pure, scientific luck, and it changed the field forever. And yet, luck or not, it solidified NGC 2770's place in the history of astrophysics. This wasn't just a galaxy producing supernovae. It was producing observable supernovae, in multiple wavelengths, with valuable data across every phase of stellar death. In a span of 9 years, NGC 2770 had become the backdrop for one of the most important supernova discoveries ever made. 3 explosions. All of the same type. In one spiral galaxy. And now, we had witnessed one of them from the very first second. The Swift satellite was never supposed to witness the birth of a supernova. That wasn't its job, and it wasn't even looking for one. Launched in 2004 by NASA, the Swift gamma-ray burst mission was built with a single primary objective: to detect and observe the most powerful explosions in the universe, gamma-ray bursts, or GRBs. These bursts are the result of extreme events such as the collapse of massive stars into black holes or the merging of neutron stars, and they emit brief flashes of gamma rays that can last from milliseconds to minutes. Swift's job was to spot these bursts in real time, then rapidly reorient itself to follow up in X-ray, ultraviolet, and optical wavelengths, giving scientists a complete look at the fleeting phenomenon. It was designed for speed and precision, capable of autonomously slewing its instruments toward a target within 20 to 70 seconds of detection. It became one of the most effective tools ever created for capturing GRBs and their afterglows. But on January 9, 2008, the satellite happened to be looking somewhere else, not at a gamma-ray burst, but at a familiar galaxy that had recently hosted a supernova. That galaxy, of course, was NGC 2770. Just 10 days earlier, SN2007 had exploded in its southern disk. The supernova had drawn interest from astronomers worldwide, and several observational campaigns were already in progress. Swift, though not typically used for supernova studies, was asked to conduct follow-up observations of SN2007 not to look for new activity, but to analyze the fading afterglow in UV and X-ray. The satellite slewed into position and began its observation run. Its X-ray telescope, XRT, started collecting data from the general region around SN2007. But just a few arc-minutes away from the coordinates of the known supernova, Swift recorded something entirely unexpected. A bright, sudden burst of X-rays flooded the detector. It lasted only a few minutes, but it was intense and unmistakably real. At first, the Swift team considered the possibility that they'd caught a faint gamma-ray burst. That would have been well within the satellite's intended mission. But there was something unusual about this burst. It didn't fit the typical GRB profile. It wasn't as brief, And it wasn't followed by the kind of gamma-ray emissions that usually accompany those colossal cosmic detonations. And it wasn't localized in a deep or distant galaxy. This was coming from the exact same galaxy they were already observing. More specifically, it was from a completely different region of NGC 2770, unrelated to SN2008. Swift had stumbled upon something else. Something new. A quick check confirmed that the X-ray burst had no prior counterpart in that part of the galaxy. No known X-ray sources, no known variable stars, no active galactic nuclei. And yet here it was, a transient, brilliant, short-lived pulse of X-rays that didn't fit the usual suspects. Astronomers dug deeper. The realization came fast. This wasn't a gamma-ray burst at all. It was a shock breakout. The very moment the core collapse of a massive star forced a shockwave through the outer layers of the star and out into space, releasing an intense but brief flash of high-energy radiation. No one had ever observed one of these in real time. Theoretical models had long predicted them. Simulations had described what they might look like. But until now, the universe had never offered up a clear example. And it had done so by pure accident. If Swift had not been observing NGC 2770 at that exact time, if its telescope had been pointed even slightly to the side, the entire event would have been missed. X-ray shock breakouts happen quickly and fade just as fast. In a span of 10 minutes, the event would have been invisible in all other wavelengths. It was like hearing the very first crack of a tree falling in a forest, before the crash, before the echo, before the dust. Just the first, sharp warning that something had changed forever. This marked the first direct detection of a shock breakout from a supernova, now officially named SN2008D. And Swift's accidental discovery turned into one of the most significant supernova observations in history. What had begun as routine calibration work ended up opening a door to a part of the supernova process that had previously been hidden from view. Following the X-ray detection, ground-based telescopes scrambled to follow up. Within hours, new optical data confirmed a rising light curve from the same position as the X-ray burst. By January 11th, only 2 days later, astronomers were already watching a fresh type IB supernova emerge from the region of the earlier X-ray signal. The link was indisputable. Swift had captured the very beginning of SN2008D, something no other satellite or telescope had ever managed to do before. The implications were immense. For one, it meant that X-ray monitoring of star-forming galaxies could become a tool not just for studying the aftermath of stellar death, but for catching the very act of core collapse. It provided insight into the structure of the progenitor star, the density of its outer envelope, the exact timing of collapse, and the way energy propagates through the body of a dying star. But more than that, it suggested that there might be other shock breakouts happening all the time, dozens or hundreds of them every year, just waiting to be caught by an eye in the right place at the right time. It raised a fundamental question. How many of these moments had we missed simply because we weren't looking? Swift's accidental discovery also highlighted something else: how small, low-budget, mission-focused satellites could yield transformational results when paired with fast coordination and open data. Once Swift's data was released, observatories worldwide pivoted to SN2008D. The Gemini Observatory, the Very Large Telescope, the Nordic Optical Telescope, and others captured every stage of its evolution. The event united the astrophysical community in a way that few supernovae ever had. It's hard not to marvel at the serendipity. A satellite looking at an old supernova inadvertently catching the birth of a new one. Two massive stars in the same galaxy, dying within days of each other, in completely different regions of space, yet tied together forever in scientific history. It was as though NGC 2770 was revealing its secrets in stages, like a book with chapters hidden behind one another, waiting for the right observer to flip the page. And the page Swift turned was historic. It wasn't just the detection of a supernova. It was the witnessing of its first breath, the luminous cry of a star collapsing in real time, seen not after the fact, but as it happened. In that moment, our understanding of stellar death changed. And all because a satellite was in the right place, at the right time, doing something it wasn't even meant to do. The sight of a supernova in the night sky is a rare, almost mythical event. To see one in a given galaxy is notable. To see two in a decade is surprising. But to see 3 type IB supernovae in the same galaxy within just 10 years? That's astonishing. And that's exactly what makes NGC 2770 so deeply unusual, not just as an isolated statistical quirk, but as a direct challenge to some of astronomy's most basic assumptions about stellar death, galactic evolution, and the nature of massive stars. To understand why this is so remarkable, consider the average supernova rate in galaxies like our own. In the Milky Way, astronomers estimate that a supernova occurs roughly once every 50 to 100 years. That includes all types, Type Ia, Type II, Type IB/C, and others. And many of those go unseen due to interstellar dust or the direction of the explosion. In nearby galaxies, the rate isn't much different, especially in spiral galaxies like NGC 2770, which aren't undergoing any unusually intense starbursts. Statistically speaking, for a typical spiral galaxy, you might expect to catch maybe one observable supernova per century, if that. Now strip that expectation down further. Among all supernovae, Type IB represents only a small fraction. They belong to the stripped envelope class, stars that have lost their hydrogen layers prior to collapse. These aren't your run-of-the-mill supernovae. They require massive progenitors, evolved in very specific ways, often in binary systems or within high-energy, windswept regions. According to surveys of nearby galaxies, Type IB supernovae constitute roughly 7 to 10% of all core-collapsed supernovae. So now, imagine the odds, not just one Type IB, but 3, in the same galaxy, and not over centuries, but within a tight 10-year window. The rarity is compounded by the consistency. Each of the 3 supernovae, SN2008D, SN2007UY, and SN2008D, were of the same subclass, Type IB. This tells us that NGC 2770 isn't just producing massive stars. It's producing a specific kind of massive star, consistently, over a relatively short span of cosmic time. It suggests a galactic environment that favors the stripping of hydrogen layers, either through intense stellar winds, binary interaction, or other mass loss mechanisms, resulting in an above-average production of progenitors primed for Type IB collapse. The timing adds another layer of strangeness. While galaxies can certainly host multiple supernovae over the course of their lives, the chance of observing 3 within 10 years in one galaxy, and all of the same subtype, stretches coincidence past its breaking point. Many astronomers have described it as a cosmic jackpot, an observational anomaly that has turned NGC 2770 into a natural laboratory for studying this elusive category of stellar death. But the oddity isn't just in the numbers. It's in how the events unfolded. SN2008D emerged quietly, detected in routine observations. SN2007UY followed nearly a decade later, brighter and better documented, and just as its light began to fade, SN2008D exploded into view, not with optical light, but with X-rays. That sequence, 3 explosions, 3 examples of a rare subclass, capped off by one of the most important supernova discoveries in history, makes the pattern not just statistically rare, but scientifically invaluable. It's important to note that other galaxies have hosted multiple supernovae in relatively short periods. Starburst galaxies like M82 or ARP-299, for example, have high star formation rates and have produced numerous supernovae across various types. But those galaxies are in a state of extreme starburst activity, forming stars at rates many times higher than the Milky Way. NGC 2770 isn't in that category. It's not undergoing any known galactic mergers, it doesn't have massive star-forming regions spread across its disk, and its overall rate of star formation is only moderately above normal. And yet, it's producing supernovae like a galaxy on overdrive. This divergence from expectation is what makes NGC 2770 so scientifically provocative. It's not just rare, it's misbehaving. It's showing that high-energy stellar deaths can cluster in a relatively calm spiral system, that stripped envelope supernovae may arise under more normal conditions than we thought, and that the processes leading to type IB collapse may be more widespread in ordinary galaxies than models have previously suggested. Astronomers have modeled the statistical odds of this happening and found them to be exceedingly low. Some estimates put the chance of observing 3 type IB supernovae in a single, non-starburst galaxy over 10 years at less than 1 in several thousand. That probability falls even further when you consider the precision of the observations, that one of those supernovae was caught at the exact moment of shock breakout, by a satellite that wasn't even looking for it. These are not odds you plan for. These are odds you marvel at. And so, NGC 2770 forces a rethinking of galactic dynamics. Perhaps the processes that lead to hydrogen stripping in massive stars are more efficient in certain environments than we've realized. Perhaps binary interactions are more common in galaxies with particular metallicities or mass distributions. Or perhaps NGC 2770 is just an outlier, a fluke, statistically improbable, but not impossible. But even if it is a fluke, it's the kind of fluke that changes everything. Each supernova on its own would be significant. But 3, together, form a dataset. A trend. A mystery. And that mystery has made NGC 2770 a case study in how stars die, not in theoretical simulations, but in the actual, unfolding sky. When astronomers first began piecing together the repeated, violent stellar deaths in NGC 2770, a nickname quietly emerged, one that would eventually become synonymous with the galaxy's identity, the Supernova Factory. And like many nicknames in science, it started as an informal label, a playful yet accurate reflection of what this unassuming spiral galaxy was doing, manufacturing supernovae at a pace that defied expectations. The term began circulating in academic circles and media reports following the discovery of SN2008D, the third recorded type IB supernova in NGC 2770 within a single decade. Before this moment, NGC 2770 was barely known outside of detailed galaxy catalogs and sky surveys. But with that third explosion, especially one observed from the moment of its ignition, everything changed. The galaxy wasn't just producing supernovae. It was doing so with a kind of consistency, a cadence, that demanded attention. Thus, the term, Supernova Factory, was born, not just a poetic phrase, but a scientific metaphor for what was happening in its spiral arms. Factories, by definition, are places of production, efficient, often repetitive, and structured. NGC 2770, in its own way, mirrored that. It wasn't chaotic like starburst galaxies, nor wildly active like those undergoing major mergers. Instead, it seemed quietly efficient. Somewhere in its vast arms, the galaxy had developed the perfect environment to turn massive stars into ticking time bombs. And then, one by one, those bombs were detonating. The use of the word factory also reflects something deeper than frequency, purposefulness. These weren't random explosions occurring by chance. They were the result of a process, a repeatable set of conditions that led to the same kind of supernova, multiple times, in a narrow time frame. All 3 known explosions were type IB, and that level of consistency told astronomers that the stars involved were likely evolving through similar paths. Whether through strong stellar winds, binary mass transfer, or both, these stars were shedding their hydrogen layers before death. That required a certain stellar makeup. It required a particular environment. It required conditions that NGC 2770 apparently provided in abundance. But what exactly made it such a hot spot for stellar explosions? The answer begins with star formation. While NGC 2770 doesn't qualify as a starburst galaxy, studies have shown that its star formation rate is moderately elevated compared to the Milky Way, especially in certain regions of its disk. These patches of gas and dust, not immediately obvious in visible light, glow brightly in the infrared and ultraviolet, signaling the presence of young, hot, massive stars. These are the progenitors of core collapse supernovae, the kinds of stars that burn through their fuel quickly and end their lives with a bang. Moreover, NGC 2770 has a population of stars that seem to fall within the ideal mass range for type IB progenitors. That's not an accident. It suggests a relatively recent wave of massive star formation, perhaps triggered by internal dynamics, spiral density waves, or even gravitational nudges from its neighboring dwarf galaxy, NGC 2770b. Whatever the cause, this wave seeded the galaxy with the kinds of massive stars that would, in just a few million years, collapse and explode. Then there's the question of stellar interactions. Type IB supernovae are often linked to binary systems, pairs of stars orbiting each other in close proximity. In these systems, one star can siphon material from its companion, stripping away the hydrogen envelope and leaving behind a bare helium core. This stripping process primes the star for a type IB explosion. The more binaries there are in a galaxy, especially tight binaries involving massive stars, the more likely it is to produce these stripped envelope supernovae. NGC 2770 may simply be a galaxy rich in such systems, either due to its metallicity, its star-forming regions, or its stellar density in certain clusters. The nickname, Supernova Factory, also caught on in the media because it was vivid and accessible. It painted a picture of a galaxy that didn't just experience explosions, it produced them, over and over, like an assembly line. In press releases, public talks, and articles, the phrase became shorthand for something incredible, a galaxy that challenged our ideas of normalcy in stellar evolution. It also came with a kind of eerie beauty. Here was a galaxy, 88 million light-years away, spinning quietly in the void, invisible to the naked eye, and yet behind that tranquil appearance it was exploding again and again. Massive stars were dying in spectacular ways, releasing their outer layers into space, forming supernova remnants that would shine for decades. The elements forged in those deaths, oxygen, silicon, calcium, iron, were being hurled into the interstellar medium, enriching the next generation of stars. NGC 2770 wasn't just a factory of explosions, it was a recycler, a builder, a storyteller of the cosmic cycle of life and death. The nickname also did something else. It placed NGC 2770 in the company of other galaxies with extreme reputations. Just as M82 is known as the Cigar Galaxy, for its unusual shape and starburst activity, or URP 220 for its ultraluminous infrared emissions, NGC 2770 earned a place in the mental gallery of galaxies that do something special, something worth watching. It became a priority target for supernova monitoring programs. Sky surveys were programmed to regularly revisit it. Robotic telescopes across the globe added it to their nightly checklists. Because now, every year that passed without another explosion became a question mark. Would it happen again? Could we catch it in time? And so the galaxy, once obscure, found itself at the center of attention, not for what it is, but for what it does. It produces destruction. It forges transformation. It turns massive stars into brief flashes of brilliance and remnants of collapsed cores. It became not just a galaxy with history, but a galaxy with a habit. Spiral galaxies are among the most beautiful and recognizable structures in the universe. Their grand, sweeping arms and luminous cores evoke the classic image of a galaxy that most people picture in their minds, a brilliant whirl of stars rotating in a cosmic dance. Yet beneath their elegant appearance lies a rich complexity of structure, evolution, and dynamics. Understanding spiral galaxies is essential to understanding where stars are born, how they evolve, and ultimately, how galaxies like NGC 2770 become sites of spectacular stellar death. NGC 2770 is a textbook example of a spiral galaxy. Located about 88 million light-years away in the Constellation Lynx, it presents the classic flattened disk shape with winding arms emanating from a central bulge. Though not as famous as the Milky Way or Andromeda, its structural anatomy is remarkably familiar. It has a luminous disk composed of stars, gas, and dust, interspersed with regions of active star formation, and a central bulge of older, redder stars. A diffuse halo likely surrounds it, made up of ancient stars and globular clusters. All of these components work together, governed by gravity and angular momentum, to create the dynamic environment in which stars live and die. To understand what makes NGC 2770 special, we must first break down the general architecture of spiral galaxies. At the center lies the galactic bulge, a spherical or slightly flattened collection of old stars. This region is typically densely packed and contains little cold gas, making it a relatively quiet zone when it comes to star formation. In many spiral galaxies, including the Milky Way, this bulge also houses a supermassive black hole, although for galaxies like NGC 2770, such a central black hole is expected to be modest in size compared to those found in active galactic nuclei. Surrounding the bulge is the galactic disk, where most of the galaxy's mass, and its activity, resides. This disk is thin compared to its width and filled with both old and new stars. It contains vast reservoirs of hydrogen and molecular clouds, serving as the raw material for star formation. Spiral arms emerge from the disk and wind outward like the arms of a pinwheel, forming graceful, trailing patterns of starlight and interstellar matter. These spiral arms are not rigid structures. They are density waves, where stars and gas temporarily crowd together like cars in a traffic jam. As gas clouds move into these denser regions, they become compressed, triggering the collapse of molecular clouds and the formation of new stars. The youngest and hottest of these stars, typically O and B type, illuminate the arms with a bluish glow, marking them as the primary sites of stellar birth. NGC 2770 fits into the classification of a late-type spiral galaxy, meaning it has well-developed spiral arms, a modest central bulge, and a relatively high amount of gas and dust. It does not exhibit the extreme bar structure seen in barred spirals like our own galaxy, nor does it show signs of a tightly wound spiral or a massive bulge that would shift it toward an early type classification. In many ways, it is average in appearance, but average, in this case, conceals a rich inner life. Images of NGC 2770 reveal loosely wound spiral arms extending outward in a graceful, flocculent pattern. The arms are dotted with clumps of brighter light, many of which are likely active H2 regions, zones of ionized hydrogen gas lit up by the ultraviolet radiation from young, hot stars. These regions are direct evidence of ongoing star formation. In visible wavelengths, the arms appear patchy and slightly asymmetric, suggesting the presence of star-forming clusters scattered unevenly through the disk. The galaxy's orientation is slightly tilted relative to our line of sight, giving us a partial top-down view of its structure. Another defining feature of spiral galaxies, including NGC 2770, is the presence of interstellar dust. This dust is not the kind that accumulates on bookshelves, but microscopic particles of carbon, silicates, and metals that absorb and scatter light. Dust is essential to star formation, as it shields gas clouds from radiation and helps them cool and condense into protostars. However, it also obscures parts of galaxies in visible light, making infrared observations crucial for seeing into dense star-forming regions. What makes NGC 2770 particularly interesting is that, despite its relatively modest size and appearance, it hosts regions of unexpectedly vigorous stellar activity. Its spiral arms seem to be fertile ground for the formation of massive stars, those with short lives and violent deaths. These stars form in dense molecular clouds, live for a few million years at most, and then explode as supernovae. The fact that NGC 2770 has produced multiple type IB Supernovi, each requiring a stripped envelope progenitor, means that it's forming not just stars, but a specific kind of star, massive, often in binaries, and prone to shedding their outer layers before collapse. Spiral galaxies like NGC 2770 also rotate. This rotation plays a crucial role in their structure and evolution. As the galaxy spins, stars and gas clouds move along its disk, cycling through spiral arms and density waves. This movement contributes to the mixing of stellar populations and chemical elements. Over time, the elements forged in earlier generations of stars, carbon, oxygen, silicon, iron, are spread throughout the galaxy, enriching new stars and planets with heavy elements. This metallicity, or the abundance of elements heavier than helium, can influence how stars evolve and die. Galaxies with higher metallicities are more likely to produce stellar winds that strip away outer layers, potentially increasing the number of type IB progenitors. In NGC 2770, the metallicity appears to be intermediate, not as high as in the most massive spiral galaxies, but not as low as in dwarf galaxies or irregular systems. This middle ground may provide just the right balance, enough metals to promote mass loss and envelope stripping, but not so much as to inhibit the formation of very massive stars. The result is a spiral galaxy quietly building the conditions for stellar detonation without tipping over into chaotic starburst behavior. There's also the matter of galactic environment. Spiral galaxies do not exist in isolation. They interact with nearby galaxies, dark matter halos, and intergalactic gas. NGC 2770 is part of a small group and has a known dwarf companion, NGC 2770b, which may play a subtle but important role in its structure. Gravitational interactions, even minor ones, can disturb the distribution of gas within a galaxy, compressing clouds and sparking new waves of star formation. If NGC 2770 has experienced recent tidal interactions with its neighbor, it may have undergone a quiet rejuvenation, an influx of fresh gas, a boost in star formation, and, as a result, an uptick in supernova activity. In this way, NGC 2770 illustrates how spiral galaxies, even those without dramatic external appearances, can harbor intense internal processes. It reminds us that a galaxy doesn't need to be warped or colliding or bursting at the seams to be interesting. Sometimes, a relatively calm, well-structured spiral can be the perfect laboratory for watching stars live and die on their own terms. And so, NGC 2770 spins on, arms full of gas, patches of dust, clusters of stars in all stages of life. It looks, from a distance, like any number of other spirals sprinkled across the cosmos. But within its elegant shape, it hides a strange pattern, a rhythm of supernovae that has earned it attention far beyond what its modest light might suggest. What began as a seemingly average spiral galaxy has proven to be anything but. Its structure, stable, ordered, rich with potential, has created a quiet storm of stellar creation and destruction. A reminder that even in the well-known territory of spiral galaxies, there are still surprises waiting to be found. While NGC 2770 holds the spotlight as the so-called Supernova Factory, it doesn't exist alone in the vast expanse of space. Nearby, quietly accompanying it in its cosmic journey, is a lesser-known but scientifically intriguing dwarf galaxy known as NGC 2770b. At first glance, this small companion might seem like an inconsequential background actor in the larger narrative of supernovae. But a closer examination reveals a potentially significant influence, one that may be subtly shaping the conditions for stellar death in its larger neighbor. NGC 2770b is a dwarf irregular galaxy, far smaller in mass and size than NGC 2770, and faint enough that it escaped detailed observation for many years. Yet its proximity to NGC 2770 makes it difficult to ignore, especially in light of the unusual frequency of supernovae in the larger galaxy. Astronomers have long suspected that galaxy interactions, especially those involving a more massive galaxy and a smaller satellite, can stimulate bursts of star formation. These bursts, in turn, can lead to an increased rate of core collapse supernovae within a few million years. And while NGC 2770b might not be violently colliding with its spiral host, the gravitational handshake between the two could be far more consequential than once believed. The key lies in the gravitational influence that NGC 2770b exerts. Even a modest gravitational tug from a nearby dwarf galaxy can disturb the delicate balance of gas within a spiral disk. These tidal interactions may not produce the dramatic warping seen in major mergers or galactic cannibalism, but they are capable of compressing gas clouds, triggering turbulence, and seeding new pockets of star formation. All of this happens quietly, subtly, and over long stretches of time, but the effects can be profound. Some observations have suggested that the southern region of NGC 2770, where two of the three supernovae erupted, shows signs of mild asymmetry in its spiral structure and star-forming regions. While this asymmetry is subtle, it may point to past or ongoing disturbances in the galaxy's disk, possibly linked to gravitational interactions with NGC 2770b. These localized distortions are often seen in galaxies that are interacting with companions. They don't always manifest as large-scale warps or visible tidal tails. Instead, they often appear as irregular patterns of gas distribution, offset arms, or concentrated star-forming clumps. NGC 2770b itself shows signs of recent starburst activity. Although far smaller than its neighbor, it glows brightly in ultraviolet light, an indicator of young, hot stars being born in rapid succession. This UV emission has attracted interest from researchers studying small galaxies with unusually high specific star formation rates. Despite its low mass, NGC 2770b is forming stars at a disproportionately high pace for its size. And if it is undergoing a starburst of its own, it raises a tantalizing possibility that a shared interaction event between the two galaxies might have triggered star formation on both sides. Such synchronized starbursts are not uncommon in interacting galaxy pairs. Even weak tidal interactions can lead to compressive flows of gas in both galaxies, especially if they pass close to each other or oscillate in a bound orbit. In this scenario, NGC 2770 may have experienced a gentle nudge, a gravitational prod that funneled gas into its spiral arms, sparked the collapse of molecular clouds, and planted the seeds of massive stars. Over the course of several million years, those stars evolved and ultimately exploded in the dramatic events we now catalog as SN1908D, SN2007 and SN2008D. It's worth emphasizing that while no clear tidal tails or bridges of gas connect the two galaxies in visible light, the invisible structure of dark matter could still bind them together in a common halo. These halos often span hundreds of thousands of light years and exert mutual gravitational forces that shape the motion and evolution of galaxies within them. The lack of a visible merger doesn't rule out a strong, slow-motion interaction happening beneath the surface. In fact, such low-level interactions might be more productive in fueling star formation over the long term than the more chaotic, short-lived mergers. Major collisions often strip galaxies of their gas and disrupt their disks. But minor interactions, especially with dwarf companions, can act like stirring spoons, agitating gas into movement without destroying the overall structure. For a spiral like NGC 2770, this could mean pockets of intense star formation within an otherwise stable disk, a pattern that fits the supernova history we've observed. Researchers have begun using advanced simulations to model interactions like the one between NGC 2770 and NGC 2770b. These simulations show that even a dwarf companion with a fraction of the mass of the primary galaxy can trigger enhanced star formation in localized regions. Depending on the orbital path, timing, and gas content, these effects can persist for tens or even hundreds of millions of years. The birth of massive stars in response to such a trigger could then ripple forward in time, creating a cluster of supernovae within a specific epoch, just as we've seen in NGC 2770. There's also an observational strategy that has grown out of this understanding. Galaxies with close companions, especially those showing mild UV enhancement, are now seen as promising candidates for supernova monitoring. NGC 2770's unusual history suggests that modest interactions, not just violent mergers, should be on our radar. In this light, NGC 2770b is not just a footnote in the story of its larger neighbor. It's a potential catalyst, one that may have quietly lit the fuse on multiple massive stars destined to die in brilliance. Whether future observations will confirm a direct causal link between NGC 2770b and the supernova activity in NGC 2770 remains to be seen. But the circumstantial evidence is compelling. We see spatial correlations between the supernovae and active star-forming regions. We see a small, active dwarf companion nearby, itself undergoing intense stellar birth. And we see a galaxy behaving as if it has been subtly stirred, not shattered. This kind of interaction, mild, enduring, and quietly influential, is often overlooked in favor of more dramatic galactic collisions. But NGC 2770 and its companion tell us that sometimes, the universe doesn't need fire and chaos to spark transformation. A gentle gravitational whisper is all it takes to set a galaxy on a path toward explosive beauty. Star formation is the heartbeat of a galaxy, The rhythmic pulse that drives its evolution, lights up its spiral arms, and seeds its future with potential supernovae. To understand why NGC 2770 has earned a reputation as a Supernova Factory, we have to dig into the very process that makes such explosive deaths possible, the birth of massive stars. And the best place to start is by asking a deceptively simple question: how quickly is NGC 2770 forming stars? At a glance, NGC 2770 might appear like a fairly average spiral galaxy. It's not bursting at the seams with new stars like some famous starburst galaxies. It isn't undergoing a major galactic collision or showing dramatic signs of interaction. Yet, it's producing massive stars, and their eventual deaths, in a way that catches the attention of astronomers around the world. The clue lies in its moderately elevated star formation rate, which, when compared to galaxies of similar type, seems just a little too productive for its own good. Estimates based on ultraviolet, infrared, and H-alpha observations place NGC 2770's total star formation rate, SFR, at approximately 1.5 to 2 solar masses per year. That means, on average, the galaxy produces the equivalent of about 1.5 to 2 suns worth of new stellar material every year. To someone unfamiliar with galactic metrics, that might not sound like much. But let's put that number into perspective by comparing it to our own Milky Way. The Milky Way is a more massive galaxy than NGC 2770, both in stellar mass and overall diameter. It stretches over 100,000 light-years across and contains upwards of 200 billion stars. And yet, its star formation rate is estimated to be about 1 to 1.5 solar masses per year, comparable to, or even slightly lower than, that of NGC 2770. In other words, NGC 2770 punches above its weight when it comes to making new stars. What makes this especially significant is that the type of stars being formed matters just as much as the total quantity. The majority of stars formed in any galaxy are low-mass stars, long-lived, faint red dwarfs that will never go supernova. Only a small fraction of newly born stars are massive enough to end their lives in catastrophic core collapse supernovae. These massive stars, typically more than 8 times the mass of our Sun, live fast and die young, usually in less than 30 million years. And it is these rare stellar giants that provide the flashpoints for galaxies like NGC 2770 to earn their supernova nicknames. While a modest overall star formation rate might not predict frequent supernova activity, a higher proportion of massive stars could change the equation significantly. Some galaxies, due to metallicity, gas density, or recent interactions, produce a top-heavy initial mass function, IMF, essentially, a population skewed toward heavier stars. If NGC 2770 is forming slightly more massive stars than average, then its supernova output would naturally be amplified, even if the overall SFR isn't dramatically elevated. There's also the matter of star formation efficiency, SFE, a measure of how effectively a galaxy converts its gas into stars. NGC 2770's efficiency appears to be somewhat higher than galaxies of comparable type and size, especially in localized regions of its spiral arms. Infrared and ultraviolet observations have pinpointed hot spots of activity, concentrated regions where dense molecular clouds are collapsing under gravity and lighting up in the blue-white blaze of young, high-mass stars. These pockets of productivity act as supernova nurseries, incubators for short-lived stars that will soon burn out in explosions bright enough to outshine their entire host galaxy. One of the tools astronomers use to analyze star formation in galaxies like NGC 2770 is H-alpha imaging, which detects the specific wavelength of light emitted by ionized hydrogen gas. This glow is a signature of star-forming regions, as it is caused by the intense ultraviolet radiation from newly formed O and B-type stars. Studies have shown that NGC 2770 has numerous active H-alpha regions along its spiral arms, particularly in the southern region where multiple supernovae have erupted. This distribution is uneven, pointing to localized bursts of activity rather than a galaxy-wide starburst event. This non-uniform star formation pattern is particularly important. Rather than forming stars evenly throughout its disk, NGC 2770 appears to concentrate its efforts in specific areas, creating stellar clusters that are rich in massive, short-lived stars. These clusters are the likely birthplaces of the progenitors for SN1909, SN2007UY, and SN2008D. And because the life cycles of such stars are so short on cosmic timescales, their deaths appear clustered in time as well as space, hence the striking appearance of multiple type IB supernovae in a brief observational window. Comparing NGC 2770 to true starburst galaxies provides further insight. Take, for example, the Cigar Galaxy, M82, which has a star formation rate closer to 10 solar masses per year, 5 times that of NGC 2770. M82 is a true factory, churning out stars so rapidly that its central regions are lit by intense, widespread ionization. NGC 2770, by contrast, is more subtle. It's not pushing the boundaries of star formation on a galactic scale, but in certain regions, its conditions are just right. And that may be more than enough. There's also growing evidence that environmental factors, like interactions with NGC 2770b, may have injected a fresh supply of cold gas into the disk or disturbed the existing gas enough to form dense clouds. These perturbations could have led to the emergence of new star-forming regions precisely in the areas where the supernovae later appeared. While the total gas mass of NGC 2770 is moderate, it may be using what it has with remarkable efficiency. In essence, NGC 2770 is a galaxy that doesn't scream with star formation, it whispers. But in those whispers, it crafts the future engines of destruction. It's a galaxy that specializes in precision, not volume. It doesn't produce hundreds of massive stars all at once. It seems to grow them deliberately, in just the right conditions, at just the right time, setting the stage for a trio of extraordinary explosions that astronomers were lucky enough to catch. When we look at star formation as a galactic ecosystem, NGC 2770 represents a balance point. It's not dormant, nor is it overwhelmed with stellar birth. It exists in a sweet spot, a level of productivity that is sustainable but still rich enough to create the necessary conditions for type IB supernovae to appear repeatedly. And that makes its star formation rate one of the most important metrics in understanding why this galaxy behaves the way it does. The numbers may not look extreme on the surface, but the outcomes speak for themselves. In 10 years, 3 massive stars reached the end of their lives, each shedding light and data into our instruments. The quiet star formation of NGC 2770 led to a cascade of death that now informs how we understand the life cycles of massive stars and the rhythms of a galaxy many millions of light years away. The key to unlocking the mystery of NGC 2770's unusual supernova activity lies not just in its gas content, star formation rate, or companion galaxies, but in the very stars that live within it. Like forensic scientists combing through the aftermath of a fire to determine what ignited it, astronomers have turned their attention to the galaxy's stellar population, searching for patterns, anomalies, and evolutionary footprints that might explain why so many massive stars in NGC 2770 seem to be ending their lives in spectacular explosions. To begin with, the stellar population of NGC 2770 is a blend of both young and old stars, typical of a spiral galaxy. Its central bulge harbors ancient, redder stars that have burned steadily for billions of years, remnants of early star formation epochs. These stars are small, cool, and stable, unlikely to go supernova and more likely to quietly fade into white dwarfs. But the outer disk and spiral arms tell a very different story. It's in the arms, those bright, curling structures dotted with UV hotspots and H-alpha emissions, that we find the real protagonists of NGC 2770's recent supernova saga, massive, short-lived stars. These stars are blue or bluish-white in color, often burning at tens of thousands of degrees Kelvin, and live no longer than a few million years. Their intense radiation and powerful stellar winds shape the interstellar medium around them, clearing out bubbles of hot gas and sometimes triggering further waves of star formation. In NGC 2770, these stars appear to be relatively abundant in specific clusters, particularly in regions south of the galactic core where 2 of the 3 known type IB supernovae occurred. These are not isolated, lone giants. They are members of compact stellar communities where the conditions are just right for producing high-mass stars. Such clusters may contain dozens or even hundreds of massive stars, many of which are bound together by gravity and evolving in parallel. Among these clusters, astronomers suspect the presence of Wolf-Rayet stars, a crucial piece of the supernova puzzle. Wolf-Rayet stars are massive, evolved stars that have shed their outer hydrogen layers due to intense stellar winds or interactions with a binary companion. What's left behind is a dense, hot core primarily composed of helium. These stripped envelope stars are exactly the kind of progenitors that can go supernova as type IB or type IC events. Their presence in significant numbers within NGC 2770 could help explain the galaxy's repeated production of this rare supernova subtype. Wolf-Rayet stars don't live long. Once their outer layers are gone, they burn through their remaining helium in just a few 100,000 years before collapsing. And that collapse is usually not quiet. When it comes, it releases a torrent of energy, sometimes visible as a classic supernova, other times shrouded in dense circumstellar material. The relatively short lifespans of these stars, combined with their propensity for violent endings, create a clustered window of time where multiple supernovae can occur in the same region of a galaxy over just a few years or decades. It's also likely that binary stars play a significant role in the makeup of NGC 2770's stellar population. Binary systems, especially those containing two massive stars, are more than just common in the universe. They may be the rule rather than the exception. And in the case of stripped envelope supernovae, binary interactions are essential. One star in the pair can siphon away mass from its companion, effectively removing the hydrogen envelope and priming it for a type IB explosion. Evidence from other galaxies suggests that the majority of type IB and IC supernovae originate in such systems. If NGC 2770 has a higher than average proportion of massive binaries, it would naturally produce more of these events. This possibility is supported by the chemical composition, or metallicity, of NGC 2770's interstellar medium. Metallicity refers to the abundance of elements heavier than hydrogen and helium in stars and gas, and it can significantly influence stellar evolution. High metallicity environments produce stronger stellar winds, helping massive stars shed their outer layers more easily. This creates favorable conditions for the formation of Wolf-Rayet stars and increases the likelihood of type IB supernovae. Observations suggest that NGC 2770's metallicity is slightly above average for a spiral galaxy of its size, supporting the idea that it has the right chemical mix to drive envelope stripping. Another clue lies in the age distribution of the stellar population. Regions that have recently formed stars will contain a large proportion of hot, massive stars that are nearing the end of their lives. If a burst of star formation occurred 10 to 50 million years ago, perhaps triggered by an interaction with its companion, NGC 2770b, then many of those massive stars would now be dying. This could explain the cluster of supernovae observed in a single decade. The clock simply ran out on a generation of massive stars born in the same star-forming wave. By mapping the locations of known supernovae within NGC 2770 and comparing them to ultraviolet and H-alpha data, astronomers have identified specific stellar neighborhoods, regions teeming with young, massive stars likely to follow in the footsteps of their exploded kin. These are not isolated events. They form a pattern, pointing to structured, wave-like star formation that sends ripples of stellar birth and death through the galaxy's disk. Even the stellar remnants left behind by supernovae offer hints about the population that created them. Depending on the mass of the progenitor, these remnants can be neutron stars or black holes. While we can't easily detect the black holes directly, the presence of pulsars or supernova remnants glowing in X-ray or radio wavelengths can give us a sense of how many massive stars ended their lives this way. NGC 2770, though not yet mapped in detail for such remnants, is a promising target for future observations with sensitive radio and X-ray telescopes. So what emerges is a picture of a galaxy that, on the surface, seems ordinary, but beneath that surface lies a stellar engine tuned for destruction. NGC 2770's spiral arms are more than just graceful structures. They are factories for massive, short-lived stars, built with the right chemistry, environment, and interactions to support a disproportionately high number of supernova candidates. It's not just that NGC 2770 forms stars, it forms the right kind of stars. Stars that shine briefly, burn violently, and die spectacularly. Stars born into tight binaries, stripped of their outer layers by greedy companions. Stars heavy with metals, pushing their hydrogen envelopes away through relentless winds. Stars that, together, create a ticking clock counting down to the next explosion. And with each new generation of these stars, the cycle renews. The gas and dust from previous supernovae enrich the interstellar medium, creating the conditions for new star formation. The heavy elements forged in stellar cores are scattered across the galaxy, building the raw materials for planets, future stars, and perhaps even life. In the end, the stellar population of NGC 2770 is not just a collection of stars, it is a cosmic narrative, playing out in real time, with each supernova marking the end of one chapter and the beginning of another. At the heart of every supernova lies a paradox: destruction that gives birth to creation, collapse that fuels expansion, and silence followed by a sudden, deafening roar across the universe. To truly understand why galaxies like NGC 2770 earn names like Supernova Factory, we must dive deep into the internal machinery of the very stars that make such cosmic violence possible. This is the anatomy of a supernova, a journey from peaceful fusion to catastrophic detonation, told in the life and death of a massive star. A supernova doesn't just happen. It begins millions of years earlier, inside a stellar nursery, where dense clouds of gas and dust collapse under their own gravity. In NGC 2770, as in many spiral galaxies, this collapse often happens along spiral arms, where the interstellar medium is compressed by density waves. Within these clouds, gravity knits together vast amounts of material, sometimes more than 8, 15, or even 30 times the mass of our Sun, forming a protostar that will eventually ignite nuclear fusion in its core. Once fusion begins, the star enters what astronomers call the main sequence phase, the longest and most stable part of its life. During this time, the star fuses hydrogen into helium in its core, releasing immense energy in the form of light and radiation. This energy pushes outward, creating an internal pressure that balances the force of gravity pulling everything inward. This perfect equilibrium can last for millions of years, though for massive stars, that lifespan is drastically shorter than for smaller ones. A massive star may live for only 10 million years or less, racing through its fuel like a fire burning through dry brush. As the hydrogen in the core is depleted, the star begins a new phase. Gravity starts to win, compressing the core even further, heating it up until it becomes hot enough to fuse helium into carbon and oxygen. For a while, balance is restored. But as the helium runs out, the process begins again. The core contracts, heats up, and begins fusing heavier and heavier elements: carbon into neon, neon into oxygen, oxygen into silicon, and so on. Each successive fuel provides less energy, burns more quickly, and offers only a brief reprieve from collapse. This sequence of fusion stages resembles the layers of an onion, with each shell representing a different element being burned in concentric circles around the core. Eventually, the core becomes rich in iron, and that's where the story turns fatal. Iron is unique among the elements. Unlike hydrogen or helium, fusing iron does not release energy, it absorbs it. So once a star begins producing iron in its core, it's like building a trap it can no longer escape. Fusion slows. Pressure drops. Gravity, no longer opposed by outward radiation, takes over entirely. And it acts fast, so fast, in fact, that what happens next takes mere seconds. The core collapses. The iron core, about the size of Earth but with the mass of the Sun, contracts in an instant. In less than a second, it shrinks to a fraction of its former size, reaching densities greater than atomic nuclei. At these extremes, the electrons and protons in the core combine to form neutrons, releasing a flood of neutrinos in a process called neutronization. The inner core stiffens into a nearly incompressible ball of neutrons, a protoneutron star. But the layers above the core are still falling inward at incredible speeds, up to a quarter of the speed of light. When they slam into the now solid core, they rebound violently. This rebound creates a powerful shock wave, which begins pushing outward, trying to blow apart the collapsing star. However, this shock doesn't have an easy time. It stalls. The energy of the shock gets sapped by the dense infalling material, and the star seems on the brink of collapsing entirely. For years, this moment was a mystery. What restarts the shock? What actually causes the explosion? Modern models suggest that neutrinos, those ghostly, nearly massless particles released in staggering numbers during core collapse, may hold the key. Though most escape without interaction, just a small fraction of them can deposit enough energy into the stalled shock wave to reignite it. This neutrino-driven explosion is one of the leading theories behind core collapse supernovae. The shock wave, re-energized, tears through the layers of the star and blasts them outward into space in a blindingly powerful display of light and matter. The result is a Type II or Type IB/C supernova, depending on how much of the outer layers remain. If the star has retained its hydrogen envelope, the explosion is classified as Type II. But in the case of NGC 2770's famous supernovae, SN1998, SN2008Y, and SN2008D, these were Type IB, meaning the star had already shed its hydrogen shell, either through strong stellar winds or by transferring material to a binary companion. Without the hydrogen, the spectrum of light from the supernova lacks hydrogen lines, allowing astronomers to classify it precisely. The presence or absence of helium lines further differentiates between Type IB and IC. These distinctions aren't just academic, they provide vital clues about the progenitor star's life and its surroundings. As the supernova unfolds, the ejected material travels outward at speeds of 10,000 to 30,000 kilometers per second, lighting up the surrounding space. The explosion releases more energy in a few seconds than the Sun will produce in its entire 10 billion year life. For a brief period, days or weeks, the supernova can outshine its entire host galaxy, making it visible across vast cosmic distances. In the aftermath, what remains depends on the mass of the original star. If the core was between about 1.4 and 3 times the mass of the Sun, it will settle into a neutron star, a city-sized object so dense that a single teaspoon of its material would weigh billions of tons. But if the core was more massive than that, gravity wins again, and the collapse continues until a black hole is born, a region of space from which not even light can escape. Meanwhile, the outer layers, rich in heavy elements forged during the star's lifetime and in the final moments of the explosion, spread out into space. These elements, carbon, oxygen, calcium, iron, gold, will mix into the galaxy's interstellar medium, seeding the birth of new stars, planets, and perhaps even life. Every atom of calcium in your bones, every atom of iron in your blood, was once forged in the heart of a dying star. And this is what makes a supernova both an end and a beginning. In NGC 2770, this cycle has repeated itself more rapidly than usual. Stars, forged in dusty clouds, evolved and collapsed in tight succession. The galaxy has become a canvas for cosmic death, a death that radiates with beauty and consequence. With each supernova, astronomers get a front-row seat to a process that shaped the universe itself. And as we peer into the next segment of this cosmic narrative, we turn our focus to one of the most extraordinary supernova events ever caught, SN2008D, and what we learned by watching a star die in real time. The explosion of SN2008D was not just a cosmic event, it was a milestone in astrophysical research. The rare opportunity to catch a supernova at the very moment of its detonation gave astronomers something they'd only dreamed of, a complete timeline of a star's death, from the instant of collapse to the weeks of fading light that followed. And in the years after the explosion, SN2008D became one of the most studied supernovae in history. Its aftermath offered an unprecedented window into the mechanics of stellar death, and challenged some of the foundational ideas scientists held about how massive stars explode. In the moments immediately after the X-ray burst was detected by NASA's Swift satellite on January 9, 2008, telescopes around the world pivoted their gaze toward NGC 2770. What they observed over the next several weeks was nothing short of a celestial unfolding, a symphony of expanding gas, changing colors, and evolving brightness known as the supernova light curve. Light curves are among the most valuable tools in astrophysics. They map how the brightness of a supernova changes over time, offering clues about the energy of the explosion, the structure of the progenitor star, and the composition of the material it ejected. With SN2008D, astronomers had a unique starting point. They didn't just catch the light curve from the time the visible explosion began. They saw it from the shock breakout, the very first flash of high-energy radiation when the collapsing core sent a shockwave racing through the outer layers and into space. The shock breakout of SN2008D lasted for just a few minutes, an ephemeral X-ray flash that otherwise would have gone unnoticed without the lucky timing of Swift's instruments. In the days that followed, the optical light curve began to rise. Initially, the light curve showed a brief, early bump, interpreted as the cooling of the outermost stellar layers heated by the breakout. This cooling envelope phase was both predicted by theory and now directly observed, offering confirmation that models of core collapse physics were on the right track. Following the early flash, the supernova entered its photospheric phase, where its luminosity was dominated by the expanding, opaque gas cloud that had once been the star's outer shell. This phase peaked in brightness about 20 days after the explosion. The shape and timing of this rise told astronomers a lot about the progenitor. It likely had a compact, helium-rich envelope typical of Wolf-Rayet stars. The absence of hydrogen in the spectrum confirmed that this was a type IB supernova, matching what had been predicted from the initial observations. But the light curve of SN2008D wasn't entirely typical. It had features that hinted at a more complex structure. For example, there was a slight asymmetry in the rise and fall, suggesting that the explosion might not have been perfectly spherical. This is important because asymmetries can affect the distribution of heavy elements, the formation of jets or clumps of ejecta, and possibly even hint at whether the core formed a neutron star or collapsed directly into a black hole. Detailed spectroscopic studies added to the picture. As the supernova faded and became optically thinner, the spectra revealed broad absorption lines of helium, oxygen, and calcium, all typical for stripped envelope supernovae. But there were also hints of deeper structures, like high-velocity ejecta moving at tens of thousands of kilometers per second. Some researchers speculated that these might be the remnants of jets, narrow outflows of material possibly created by rotation or magnetic fields during the collapse. This was particularly exciting because it brought up the possibility of a continuum between supernovae and gamma-ray bursts, GRBs. While SN2008D was not associated with a GRB, the fact that it was first detected in X-rays and showed signs of asymmetry made some wonder if it was a kind of failed GRB, or a lower-energy cousin to the hyperenergetic supernovae often linked to long GRBs. These theories remain speculative, but SN2008D forced scientists to confront the idea that not all stellar deaths fit neatly into predefined categories. In the months following the explosion, astronomers continued to monitor SN2008D across multiple wavelengths: optical, infrared, and radio. The infrared observations helped track the cooling of the ejecta and the formation of new molecules, while radio telescopes picked up on interactions between the supernova shockwave and the surrounding circumstellar medium, CSM. These radio signals are crucial because they trace the mass loss history of the star in the final stages before collapse. By modeling the strength and evolution of the radio emission, researchers inferred that the progenitor of SN2008D had lost material through a stellar wind, steady streams of gas expelled into space before the final collapse. This mass loss, likely driven by intense radiation pressure and perhaps binary interaction, left behind a shell of gas that the supernova later slammed into, creating a radio-bright shock front. That impact revealed not only the structure of the surrounding space, but also the conditions that the dying star experienced in its final tens of thousands of years. Another area of research focused on the nucleosynthesis products, the elements formed during the explosion. The presence of certain isotopes, like nickel-56, can be inferred from the brightness and shape of the light curve. SN2008D's brightness indicated that about 0.07 solar masses of nickel-56 had been synthesized and ejected in the blast. As this radioactive nickel decayed into cobalt and then iron, it powered the fading tail of the light curve, another standard feature of core-collapse supernovae. But SN2008D also pushed astronomers to refine their models in new directions. For instance, it demonstrated the importance of early detection and rapid response. Catching the shock breakout was largely a stroke of luck, but it galvanized the astronomical community to develop new surveys and telescopes specifically designed to catch supernovae in the earliest possible moments. Missions like Ultrasat and new ground-based surveys like Zwicky Transient Facility, CTF, and the Vera C. Rubin Observatory's LSEST are direct descendants of the science that SN2008D inspired. Even years after the explosion, SN2008D continues to be a rich dataset for testing and revising theories of stellar evolution. It has been used as a benchmark event in dozens of papers, compared against other type IB supernovae, and modeled in 2D and 3D simulations. Its legacy is not just in the data it left behind, but in the shift it caused in how we approach transient sky phenomena. More than just an event, SN2008D became a case study, a cosmic autopsy that began at the moment of death and traced every stage of the stellar corpse's evolution. Its shock breakout taught us about the birth of supernovae. Its light curve traced the path of a star's explosion. Its spectra revealed its internal composition. And its ongoing radio afterglow continues to whisper the final secrets of a star that once burned brightly, 88 million light-years away. It was not the brightest, nor the most energetic, nor even the most unusual supernova ever recorded. But it was caught in the act, and that simple fact changed everything. In the grand cosmic theater of stellar death, not all supernovae are created equal. Their classifications, type I, IB, IC2, are more than just labels. They are windows into the life stories of the stars that exploded and the environments in which they were born. In the case of NGC 2770, what has truly intrigued astronomers is not just the frequency of its supernovae, but their specific type. All three recorded supernovae in this galaxy over a 10-year span, SN1999A, SN2007 and SN2008D, were type IB. This is no ordinary occurrence. Type IB supernovae are not the most common kind, so having three of them erupt in a single galaxy, in such a short time, raises a compelling astrophysical question. Why type IB, specifically? To answer that, we must first understand what defines a type IB supernova. In simple terms, it's a core-collapse supernova, the violent death of a massive star that has exhausted its nuclear fuel. But what sets type IB apart is the absence of hydrogen in its optical spectrum. This tells us something vital. The progenitor star had somehow lost its outer hydrogen envelope before it exploded. That's a major clue about the kind of stars NGC 2770 is producing, and the conditions in which they're evolving. Massive stars are born with layers. At their core, they burn hydrogen into helium. When that runs out, they move on to fusing heavier elements, progressing toward carbon, neon, and so on until iron seals their fate. Normally, a massive star's outermost layers are made of hydrogen, but in type IB progenitors, that hydrogen layer is gone by the time of collapse. Theories suggest two main paths for how this happens: stellar winds or binary mass transfer. In environments with high metallicity, meaning the gas from which stars form contains a significant amount of elements heavier than helium, massive stars develop stronger stellar winds. These winds, driven by radiation pressure, can peel away the star's hydrogen envelope over time, leaving behind a naked helium core. NGC 2770 is believed to have a moderately high metallicity, especially in its star-forming regions. This makes it more likely that massive stars here will shed their outer layers before they die, making them prime candidates for type IB or IC explosions. But metallicity alone doesn't tell the whole story. There's also the binary connection, a crucial, and perhaps dominant, factor. Recent studies suggest that a majority of massive stars are in binary systems, and in many of those systems, the stars are close enough to exchange mass. In these cases, one star can siphon material from its companion, effectively stripping it of its hydrogen envelope even if stellar winds alone wouldn't have been strong enough. What's fascinating about NGC 2770 is that its stellar population seems to favor the birth of such close binary systems. This could be due to the conditions in its molecular clouds, the temperature, density, and turbulence of the gas, all of which influence how stars form and whether they do so in pairs. So what we see in NGC 2770 is a stellar environment finely tuned for producing stars that die as type IB supernovae. There's enough metallicity to support strong winds, and enough binary systems to allow envelope stripping via mass transfer. Together, these factors create an unusually high likelihood that when a massive star reaches the end of its life, it will explode not as a Type II supernova, with its hydrogen envelope intact, but as a Type IB, hydrogen-poor, helium-rich, and optically distinct. This specificity tells us a lot about the star formation history of the galaxy. For instance, Type IB progenitors have shorter lifespans than many stars, often just 10 to 20 million years. The fact that we've observed 3 Type IB events in a decade suggests that NGC 2770 experienced a burst of massive star formation roughly 10 to 30 million years ago. That starburst wave would now be reaching its dramatic conclusion, with stars dying off in quick succession. Another intriguing factor is that all 3 Type IB supernovae in NGC 2770 occurred in or near active star-forming regions. This supports the idea that these explosions are not randomly distributed, but closely tied to recent star formation. It also implies that these are not ancient, wandering stars that drifted into the outskirts of the galaxy to die. They are young, massive, native-born stars, ending their brief lives in the very regions where they were formed. And then there's the question of Type IC, a close cousin to Type IB. Type IC supernovae also result from stripped envelope stars, but they lack both hydrogen and helium in their spectra. That raises the question, why hasn't NGC 2770 produced any of those, or at least not any we've detected? It could be coincidence, or it might suggest that most of the progenitor stars in NGC 2770 lose only their hydrogen, not their helium layers. This could hint at intermediate strength winds or partial binary interactions, just enough stripping to make a Type IB, but not so much to expose the carbon-oxygen core that would lead to a Type IC. This nuance matters. It speaks to the fine balance of stellar evolution that NGC 2770 seems to maintain, a balance influenced by everything from gas density and metallicity to binarity rates and rotational velocities. It suggests a galaxy where the physics of star formation doesn't just favor massive stars, but massive stars with the precise evolutionary pathways to end their lives as Type IB explosions. Moreover, the repeated detection of Type IB events in one galaxy offers a statistical anomaly that's hard to ignore. In the broader universe, Type IB supernovae are less common than Type II, which are the dominant form of core collapse supernovae. The chance of seeing 3 Type IB events in one galaxy over just 10 years is remarkably low, unless that galaxy has some special conditions making these explosions far more likely than in the average galactic environment. NGC 2770 has become something of a natural laboratory for studying these conditions. By comparing it to other galaxies, those that produce a broader mix of supernova types or those that have never been caught hosting a supernova at all, astronomers are piecing together a clearer picture of how stellar environments influence the death of stars. It's like comparing the flora of different biomes. One galaxy grows roses, another orchids, and NGC 2770 seems to grow nothing but the same fiery bloom, Type IB. Understanding why this happens isn't just academic. It helps refine population synthesis models, which are used to predict how many stars of each type should exist in a given galaxy, and what kind of supernovae we should expect to see. These models are crucial for interpreting data from distant galaxies, where individual stars can't be resolved, and supernovae are one of the only observable signatures of stellar death. In short, NGC 2770's consistent production of Type IB supernovae is more than a curiosity, it's a signal. A signature of its inner workings. It tells us about the youth of its massive stars, the chemistry of its gas, the relationships between its binaries, and the delicate evolutionary trajectories that lead to explosive ends. It's a galaxy where the dice of stellar fate seem weighted, favoring a particular kind of cosmic finale. And in doing so, it doesn't just shed light on its own inner mechanics, it illuminates a broader truth about the universe, that the death of stars is not merely a matter of chance, but a consequence of precise, measurable conditions, shaped by the invisible hands of time, chemistry, and gravitational entanglement. Identifying the precise star that exploded in a distant galaxy is a bit like trying to find the exact tree that fell in a vast, ancient forest, after the fire has already consumed everything. Yet astronomers have attempted to do exactly that with the supernovae in NGC 2770. And while challenging, the effort to identify the progenitor stars, the ones that died to produce SN2009, SN2007 and SN2008D, has not only yielded intriguing clues about these specific events, but has also advanced the science of stellar forensics. The search begins with pre-explosion images. Thanks to extensive sky surveys and archival observations from powerful telescopes like the Hubble Space Telescope, the Sloan Digital Sky Survey (SDSS), and ground-based observatories, there's a chance that the region of space where a supernova later appears had already been imaged before the explosion. If a progenitor star was bright enough and not too obscured by dust, it may have left its fingerprint, a visible light source in the exact coordinates where the supernova would later erupt. This is where astronomers began their work for NGC 2770 supernovae, particularly SN2008D, the best documented of the three. Given how suddenly SN2008D was detected in X-rays, astronomers quickly scoured the archives for pre-explosion images of its host region. They did, in fact, find such images, but no point source was detected at the explosion site. In other words, no obvious progenitor star was visible in the earlier photos. At first, this might seem like a dead end. But in astronomy, absence often speaks volumes. If a progenitor star was not seen in pre-explosion data, that allows researchers to set upper limits on its luminosity, and therefore estimate its mass and type. Based on the limiting magnitudes from deep images taken by the Hubble Space Telescope and other observatories, the star that became SN2008D must have been less than about 20 solar masses and likely heavily obscured by dust. This range fits well with the theoretical expectations for a Wolf-Rayet star, a type of stripped envelope massive star that has shed its hydrogen layer and sometimes even its helium layer, priming it to explode as a type IB or IC supernova. Wolf-Rayet stars are extremely hot but can be optically faint because of their small size and strong ultraviolet output. They also tend to reside in dusty, star-forming regions, which can further obscure them in visible light. So, even if the progenitor of SN2008D was present in archival images, it could have been buried under too much dust or simply too faint to detect in visible bands. To overcome this, astronomers turn to infrared and X-ray data, since those wavelengths are better at penetrating dust. While no pre-explosion infrared detection of the progenitor was confirmed, models constrained by the data suggest a star with a mass between 15 and 25 times that of the Sun, consistent with a helium core star, such as a late-stage Wolf-Rayet or a stripped star in a binary system. Another avenue of investigation was through spectral modeling and light curve analysis. By studying the chemical composition and expansion velocity of the ejecta from SN2008D, researchers inferred that the progenitor had lost its hydrogen envelope, and possibly some or all of its helium as well. The amount of nickel-56 produced, about 0.07 solar masses, also offered constraints on the progenitor's core mass. Simulations of such explosions matched best with a moderate mass Wolf-Rayet star, again supporting the idea that SN2008D was the final act of a stripped massive star rather than a red or blue supergiant. In the case of SN2007 similar efforts were made to identify a progenitor star, though fewer observations were available. The explosion occurred in a region with substantial dust and star formation, further complicating any archival detection. Like SN2008D, No progenitor was directly observed, but the characteristics of the supernova were modeled and matched to known stellar evolutionary tracks. Again, the data pointed to a stripped envelope star, either through wind loss or binary interaction, likely less than 25 solar masses. SN2008D, the oldest of the three, was observed in the early days of the supernova monitoring era, and unfortunately, few high-resolution images exist of its pre-explosion site. Nonetheless, researchers have revisited its location using modern instruments and better calibration to improve positional accuracy and look for any surviving traces of the progenitor. While no clear identification has emerged, SN2008D is considered part of the same pattern, a type IB explosion likely caused by a Wolf-Rayet star or an evolved massive star in a close binary system. In addition to image searches, another strategy has been to examine the stellar environment around each supernova site. Stars rarely form in isolation. Instead, they are born in clusters or associations with other stars of similar age and composition. By studying the light and spectra from the region around each supernova, astronomers can estimate the age of the stellar population, and therefore the likely age and mass of the progenitor. For instance, if the nearby stellar population is only 10 million years old, then the progenitor star must have been massive enough to evolve and die in that time frame, likely at least 20 solar masses. This method, though indirect, helps refine the likely range of progenitor masses and rules out other possibilities, such as white dwarfs or lower mass stars that take billions of years to evolve. But identifying progenitors is not only about tracing a supernova back to its source, it's about understanding the evolutionary pathways that lead to these violent endings. Are all type IB supernovae caused by Wolf-Rayet stars, or are binary systems the dominant source? Are the progenitors of SN2008D and SN2007 isolated massive stars, or were they part of close binary systems, slowly stripped of their outer layers by gravitational companions? These questions remain at the cutting edge of stellar astrophysics. In fact, the mystery of binary interaction is now seen as one of the most pressing in this field. If many massive stars are in binaries, and if binary mass transfer is more efficient than previously believed, then it may explain why stripped envelope supernovae like those seen in NGC 2770 are more common than expected from single-star evolution alone. Ultimately, the effort to find the exact stars that exploded in NGC 2770 continues, combining every possible tool: image archives, infrared surveys, spectral modeling, radio observations, and deep optical data. While no progenitor star has yet been definitively identified, each constraint, each non-detection, and each model fit narrows the possibilities and refines our understanding. And perhaps the most exciting prospect of all is this: we might catch the next one. With NGC 2770 being closely monitored and our telescopes now more powerful and sensitive than ever, the next supernova may not only be detected in real time, but its progenitor might already be visible in archival or ongoing observations. The next dying star may already be waiting in a telescope's field of view, quiet, unremarkable, and destined for cosmic fireworks. In the realm of cosmic cataclysms, the moment of a supernova's ignition is arguably the most elusive. It is the very instant a star's core collapses and a shockwave rips through its outer layers, ultimately bursting into space with the power of billions of suns. This phenomenon, called the shock breakout, is so brief and so difficult to catch that for decades, it existed only in theory and models. But then, unexpectedly and without warning, SN2008D changed that forever. It gave us a direct view of the shock breakout, captured in real time by an orbiting observatory, and became the first supernova ever witnessed in this critical phase. This singular observation would go on to reshape how we detect, study, and understand stellar death at its most fundamental level. To understand why the shock breakout is so important, we must first understand what it is. When the core of a massive star collapses, gravity compresses it so violently that it rebounds and generates a powerful shockwave. This shockwave begins deep inside the star, traveling outward through layer after layer of increasingly diffuse material. As it moves, it heats the stellar material to extreme temperatures, millions of degrees, causing it to glow. But while this heating is happening, the outer layers of the star are still opaque. The light cannot yet escape. Then, as the shockwave reaches the outermost edge of the star, it slams into material that is tenuous enough for photons to finally break free. This is the moment of shock breakout. In theory, it manifests as an extremely short-lived flash of high-energy radiation, usually ultraviolet or X-rays, depending on the size and composition of the star. The entire event may last only a few seconds to a few minutes, and is over before most telescopes even have a chance to respond. That's why, for decades, it had never been directly observed. Until January 9, 2008. NASA's SWIFT satellite was in orbit at the time, designed to detect gamma-ray bursts and rapidly alert telescopes around the world. That day, it was observing NGC 2770, not looking for supernovae, but monitoring the galaxy for the afterglow of an unrelated gamma-ray burst. While watching the galaxy's outer arm, SWIFT's X-ray telescope, XRT, detected an unexpected, sudden spike in X-rays. It lasted just a few minutes and then faded. At first, scientists weren't sure what they had seen. Was it a gamma-ray burst after all? A flare from a previously unknown black hole? Or some fluke of instrumentation? But when telescopes on Earth turned their eyes to the same patch of sky in the hours and days that followed, they witnessed the birth of a new supernova, SN2008D. The light from the explosion was still rising in the optical, meaning the event had just occurred. The pieces clicked together. The X-ray spike wasn't an afterglow. It was the shock breakout, the very moment the star exploded. This was groundbreaking. For the first time in human history, we had captured the earliest possible signal of a core-collapse supernova in action. It was as if we had seen the match strike before the blaze. The X-ray signature of SN2008D's shock breakout was brief but powerful. It lasted roughly 5 minutes, with a total energy release equivalent to about 10 ergs, or 10 million times more energy than the Sun emits in 1 second. This was consistent with theoretical predictions of a shockwave emerging from a compact progenitor, likely a Wolf-Rayet star, a stripped core with a small radius and dense outer envelope. But the data offered much more than just confirmation. The exact timing, duration, and spectral energy distribution of the shock breakout revealed new insights into the explosion mechanics. For instance, the width of the X-ray pulse suggested the outer envelope was denser than expected. This supported models where binary mass transfer or strong stellar winds had shaped the star's structure before collapse. Moreover, the shape of the X-ray pulse, the rise and fall, hinted at asymmetry in the explosion. The shock may not have emerged uniformly from the surface but may have pushed out more forcefully in one direction than another. This supported the growing theory that core-collapse supernovae are often lopsided or jet-like, rather than perfectly spherical. Even the delay between the shock breakout and the peak of the optical light curve, about 19 days, was informative. It allowed scientists to better model the cooling phase, where the outer layers expand and shed their heat before radioactive decay becomes the dominant energy source. This cooling envelope emission, detected thanks to the timing of the shock breakout, helped constrain the progenitor's radius and the explosion energy. But perhaps most importantly, SN2008D's shock breakout proved that such events could be caught. Until then, astronomers had hoped future space missions like the James Webb Space Telescope or wide-field UV surveys might detect a shock breakout one day. SN2008D showed that it could happen accidentally, with existing instruments, given the right alignment of fate and telescope aperture. The implications rippled across the astronomical community. Suddenly, the idea of building dedicated early warning systems for supernovae gained traction. Telescopes began to develop rapid response protocols, ready to follow up on any transient event that might turn out to be an early-stage supernova. Programs like the Zwicky Transient Facility (CTF) and future projects like the Vera Rubin Observatory's LSSD adopted design parameters that would allow them to catch more of these critical early phases. Researchers also began to re-evaluate past supernovae, wondering if archival X-ray or ultraviolet data might have captured faint shock breakout signals that went unnoticed. A few tantalizing candidates were identified, but none as clear-cut as SN2008D. Theoretical models also evolved. Before SN2008D, simulations of shock breakouts had to rely heavily on assumptions. Afterward, they could be calibrated with real data, refining our understanding of opacity, photon diffusion, and the behavior of light in rapidly changing stellar environments. The case of SN2008D became a benchmark for supernova modeling, cited in dozens of papers and serving as the gold standard for what a shock breakout could look like in observational terms. And then came the philosophical shift. For decades, astronomers had viewed supernovae as phenomena caught after the fact, studied in the glow of their aftermath. SN2008D changed that perspective. It reminded us that if we look fast enough, and in the right place, we can catch stars in the act of dying, not just after they are gone. This opens the door to an entirely new kind of astrophysics, real-time stellar death watch. In essence, SN2008D's shock breakout gave us the cosmic equivalent of witnessing a heart attack in real time, rather than examining the body afterward. It was raw, unfiltered data from a moment most stars take with them into darkness. And it came from NGC 2770, a galaxy that continues to whisper its violent secrets across time and space. NGC 2770, once an obscure spiral galaxy in the Constellation Lynx, has in recent years ascended to an unexpected status in the world of astrophysics, a galaxy that helped revolutionize how we understand the most powerful stellar deaths in the universe. Through its remarkable production of type IB Supernovi, particularly the landmark event of SN2008D, this unassuming galaxy has become a cornerstone in the study of supernova mechanisms, offering astronomers a real-time laboratory to test, refine, and even challenge long-standing theories about how massive stars die. The most immediate and impactful contribution NGC 2770 made to supernova research was, of course, the accidental observation of the shock breakout of SN2008D. Prior to this event, the shock breakout had only existed as a theoretical phase in the timeline of a supernova's evolution. Astronomers knew that when the collapsing core of a star sent a shockwave outward through its layers, it should release an ultra-short burst of high-energy photons, primarily in the X-ray or ultraviolet range, just before the star exploded in visible light. But because this phase was so brief and unpredictable, it had never been directly captured. When Swift detected that flash in 2008, astronomers had a real shock breakout signature for the first time. That alone was a paradigm shift. It confirmed that this ephemeral stage was not only real but also observable, opening the door to a new class of studies focused on the very earliest moments of stellar explosions. SN2008D became the first time a supernova's clock could be timed with precision, from the very moment it went off to the final fade of its light curve months later. This shifted observational strategies around the world, encouraging real-time, multi-wavelength monitoring and inspiring a new generation of transient detection technologies. But beyond the sheer novelty of this detection, NGC 2770's trio of type IB supernovae also created a dataset that was unusually consistent in supernova type, explosion dynamics, and galactic environment. This consistency allowed astronomers to compare and contrast the details of multiple type IB supernovae occurring under nearly identical galactic conditions. Such uniformity is rare in supernova science. Normally, events are studied across multiple galaxies with varying star formation rates, metallicities, and interstellar environments, all of which complicate interpretation. But here, in one galaxy, scientists were able to examine the same kind of stellar death multiple times, like repeating an experiment with slightly different variables. This consistency helped refine our understanding of the stripped envelope supernovae, specifically type IB. These events, defined by the lack of hydrogen in their spectra, were often hypothesized to originate from Wolf-Rayet stars or massive stars in binary systems that had lost their outer layers. But what NGC 2770 revealed was how common these pathways might be in a galaxy with the right ingredients: moderate metallicity, active star formation, and possibly a high frequency of massive binary systems. The galaxy effectively showed astronomers that the progenitor environment matters a great deal. Supernovae aren't just random stellar deaths, they are expressions of their surroundings. SN2008D, for instance, gave unprecedented access to the early cooling phase that follows the shock breakout. Observing this period allowed researchers to model how energy was deposited in the outer layers, how quickly the gas expanded, and how the star's composition shaped the emitted spectrum. Combined with X-ray, optical, infrared, and radio follow-up, SN2008D became a case study in multi-wavelength supernova evolution. Each of these wavelengths contributed different pieces of the puzzle. X-rays probed the shock itself, optical telescopes traced the light curve and spectrum, infrared studies observed cooling ejecta and dust formation, while radio telescopes followed the interaction of the blast wave with surrounding material. These combined observations provided a comprehensive picture of what happens after a core collapses, a kind of astrophysical autopsy that was as detailed as it was instructive. For example, the presence and behavior of nickel-56, the radioactive isotope that powers the supernova's fading light curve, could be precisely measured in SN2008D. This helped refine our understanding of nucleosynthesis, the process by which supernovae forge the heavy elements that enrich galaxies and form the building blocks of planets and life. Even the asymmetry detected in the explosion, evident in the early optical polarization and X-ray signal, hinted at more complex dynamics within the core collapse mechanism. Instead of a neat spherical detonation, SN2008D and possibly the others in NGC 2770 may have exploded with significant directional bias, meaning that rotation, magnetic fields, or jets could have played a role in shaping the blast. This bolstered the idea that many supernovae are fundamentally asymmetric, possibly linking them to more exotic phenomena like long-duration gamma-ray bursts or failed supernovae that collapse directly into black holes. Another contribution NGC 2770 made to supernova research was to inspire observational vigilance. After the 2008 discovery, astronomers began to monitor the galaxy more carefully, hoping to catch another explosion in the act. This created one of the earliest examples of a targeted supernova watch list, where astronomers keep a careful eye on certain galaxies known for high activity. It shifted thinking from broad all-sky surveys to a blend of targeted and wide-field observation, particularly for galaxies with histories of multiple core collapse events. Additionally, studies of NGC 2770's environment, especially the regions surrounding the supernova sites, gave scientists deeper insight into the kinds of stellar populations that lead to type IB events. By analyzing the colors, spectral lines, and star cluster ages in these regions, astronomers concluded that the progenitor stars were young, massive, and likely part of compact, short-lived starburst regions. These findings fed directly into simulations and stellar evolution models, providing real-world constraints on theoretical predictions. The galaxy's interaction with its dwarf companion, NGC 2770b, also became an interesting case study in how galactic interactions might drive enhanced star formation and, by extension, supernova rates. The theory that interactions between galaxies can stir up gas, trigger new generations of massive stars, and thereby increase the frequency of core collapse supernovae gained a real example in the NGC 2770 system. This encouraged researchers to look at other galaxies with similar interactions and check whether they too were hotspots for explosive stellar deaths. More broadly, NGC 2770 contributed to the conceptual redefinition of a supernova factory, not as a chaotic, overactive starburst galaxy like M82 or ARP-299, but as a moderately active spiral galaxy whose conditions just happened to align for repeated massive star deaths. This was surprising. It meant that you didn't need extreme galactic environments to produce multiple supernovae in a short time, just the right combination of metallicity, star formation rate, and stellar mass function. That subtlety changed how astronomers think about the distribution of supernova events across the cosmos. And finally, NGC 2770 served a psychological and symbolic role in the astrophysics community. It was a reminder that groundbreaking discoveries can happen in ordinary places, that something monumental can be waiting in a patch of sky overlooked for decades. It reinvigorated interest in spiral galaxies as active sites of transient phenomena and inspired a broader search for quiet factories, places in the universe that don't look dramatic at first glance, but where stellar lives are ending in spectacular fashion. Through 3 supernovae, especially one caught at the moment of ignition, NGC 2770 offered a complete narrative arc: death foretold, death observed, death understood. And in doing so, it moved us closer to answering the question that has haunted astronomy since its earliest days: how do stars die? With NGC 2770's help, we now know, not with silence, but with a flash, a blast, and a story written in the stardust left behind. As astronomers stared at the glowing remnants of yet another supernova in NGC 2770, a quiet yet unsettling question began to rise among them. Was this galaxy simply lucky, or perhaps, more fittingly, unlucky, in its rapid-fire display of stellar deaths? Or was something deeper going on beneath its spiral arms? Could this streak of 3 type IB supernovae in just 10 years be chalked up to cosmic coincidence? Or did NGC 2770 host a hidden set of conditions that made such violent events inevitable? Statistically speaking, the odds of observing 3 core collapse supernovae in a single galaxy over the course of a decade are already quite low. But to have all 3 be type IB, a subtype that's notably less common than the more typical hydrogen-rich type 2, pushes those odds even further into the realm of the improbable. Most galaxies of NGC 2770's size might expect to see one supernova every few decades, and even then, the types tend to vary. Yet here, in this quiet spiral, astronomers were served a trio of nearly identical explosions. The likelihood of such a run, based on population models and observed rates, is less than 1 in several thousand. On paper, that makes it tempting to call it a fluke, a statistical outlier, a galactic lottery win. But science rarely settles for the explanation of chance when patterns begin to emerge. An NGC 2770's supernova streak doesn't just defy the average. It seems to tell a story about how specific galactic environments can bend the odds in favor of frequent, narrowly defined cosmic cataclysms. To start, we must revisit what's known about NGC 2770's galactic profile. It's a spiral galaxy, similar in overall appearance to the Milky Way. It's not a starburst galaxy like M82, nor is it in the throes of galactic collision like ARP 299. On the surface, it's not the kind of place you'd expect such supernova fireworks. But as astronomers dug deeper, they began to notice that NGC 2770 had some unassuming peculiarities that may have quietly fueled its deadly record. One key clue lies in its modest but active star formation rate. Though NGC 2770 isn't a chaotic stellar nursery, it still bursts new stars at a rate just slightly above what we see in our own Milky Way. And importantly, this star formation isn't evenly spread out, it's concentrated in specific regions, particularly along its outer spiral arms. This suggests pockets of locally enhanced star-forming activity, regions where clusters of massive, short-lived stars are born in greater numbers than average. In astronomical terms, even slight upticks in the birth rate of massive stars can dramatically increase the odds of witnessing multiple supernovae in a short time frame. But this alone doesn't explain the specificity of type IB. To understand that part, we have to consider metallicity, stellar population age, and binary interaction frequency, a trio of factors that can tip the evolutionary scale toward hydrogen-stripped stars. NGC 2770 appears to have moderate metallicity, particularly in the star-forming regions where its supernovae have occurred. This is important because higher metallicity enhances stellar wind strength. These winds can blow off the outer hydrogen envelopes of massive stars over time, leaving behind a stripped helium core, precisely the kind of progenitor that leads to a type IB explosion. Combine this with close binary systems, where a companion star can also siphon off material, and you have a galaxy predisposed to producing naked helium cores in substantial numbers. So while randomness can't be entirely ruled out, these ingredients suggest a more nuanced conclusion. NGC 2770 may not be an accident, it may be optimized. There's also the matter of galactic interaction. NGC 2770 has a known dwarf companion, NGC 2770b, with signs of recent or ongoing tidal interaction. Though subtle, such gravitational tugs can stir up gas within the spiral disk, triggering waves of star formation in previously dormant regions. Even minor gravitational nudges can be enough to compress cold molecular gas into collapsing clumps, the kind that form massive stars destined for short, explosive lives. If this interaction began several tens of millions of years ago, it could have seeded a wave of supernova-ready stars that are now reaching the ends of their lives right on schedule. That timing aspect is essential. All three supernovae observed in NGC 2770 occurred over a tight temporal window, just 10 years between the first and third event. But their progenitor stars likely formed at the same time, in a single wave of enhanced star formation that took place roughly 10 to 30 million years earlier. These stars, all massive and short-lived, would have matured almost simultaneously. Their deaths, while staggered in human terms, represent a burst of stellar death from a single epoch of star birth. This kind of temporal clustering is another reason to doubt pure coincidence. It's not just that NGC 2770 happened to have three supernovae. It's that they fit a pattern, both in type and in the time frame of their demise. Such synchrony suggests cause and effect, not just chance. Still, the question remains, if NGC 2770 can do this, are there other galaxies just like it, hiding in plain sight? Some astronomers have suggested that many so-called quiet galaxies may be quiet only because we haven't looked closely enough. Supernovae are transient by nature, they come and go quickly. If a galaxy isn't being monitored continuously, especially across multiple wavelengths, it's easy to miss such events. The case of SN2008D, detected entirely by accident, proves this point. Had Swift not been pointing at that part of the sky, we might never have known the explosion occurred. It raises the possibility that the universe is full of supernova factories we simply haven't recognized yet. Galaxies that look average, even sleepy, but which harbor the precise stellar environments needed to produce rapid-fire supernovae under the radar. In this sense, NGC 2770 may be less of an anomaly and more of a prototype, a galactic profile that we can now search for in others. Even so, chance will always play a role. In any probabilistic system, rare events do sometimes happen. A coin can land on heads 5 times in a row. A single star cluster might randomly produce 3 massive binaries that all end as type IB Supernovi. NGC 2770's behavior, while increasingly understood through the lens of physics, could still be an outlier on the edge of a probability curve. But even if coincidence played a part, it was not pure chance. It was structured randomness, a rare alignment of factors that tipped the balance toward repeated stellar explosions. Metallicity, binarity, localized starbursts, and possible galactic interaction all stacked the deck, making the galaxy more likely than average to produce the deadly spectacle it became known for. The dance of galaxies is one of the universe's most silent and powerful forms of communication. When two galaxies approach each other, whether it's a slow gravitational flirtation or a full-blown collision, the results can be spectacular. Gas clouds compress, magnetic fields twist, and entire generations of stars are born, live fast, and die young. In the case of NGC 2770, this cosmic choreography may be playing out with its dwarf companion, NGC 2770b. And the evidence suggests that their gravitational interaction could be doing far more than just subtly tugging at spiral arms. It might be triggering waves of star formation that are directly fueling its supernova productivity. At first glance, NGC 2770b might seem unremarkable, a small, irregular dwarf galaxy located near the larger spiral of NGC 2770. It doesn't have grand sweeping arms or a luminous core. But dwarf galaxies are notorious agitators in galactic ecosystems. Because of their low mass and chaotic structure, they can be easily influenced by the gravity of larger galaxies. But they can also exert influence in return, especially if they plunge through gas-rich regions or disturb fragile spiral disk structures. Astronomers have observed signs that NGC 2770 and its smaller neighbor are not merely passing ships in the night. There are subtle distortions in NGC 2770's outer spiral arms, an asymmetry not usually seen in isolated spiral galaxies. These warps and ripples in the disk suggest a recent tidal interaction, one where the smaller NGC 2770b may have either skirted the edges of the spiral, or even passed through its outer regions. Such interactions can have profound effects on a galaxy's interstellar medium. As galaxies tug at each other gravitationally, they compress gas clouds, driving turbulent motions that would otherwise be absent. These compressed regions often become stellar nurseries, birthing massive, short-lived stars that burn out and explode within tens of millions of years. It's a well-documented phenomenon. Galaxies with companions, even minor ones, often exhibit enhanced star formation in their outskirts or in localized bursts. NGC 2770 fits this pattern suspiciously well. While not undergoing a full-blown starburst event like we see in more violent mergers, it shows elevated star formation rates in specific regions, particularly in the arms where its supernovae have been observed. These regions don't show signs of being triggered by internal processes alone. The locations and timing suggest an external catalyst, likely a passing or plunging companion. Even more intriguing is the possibility that NGC 2770b's interaction didn't just stir gas but may have also restructured gas flows within NGC 2770. Galaxy simulations have shown that minor companions can induce radio gas inflows, channeling diffuse hydrogen from the outer halo toward the inner disk, where it can cool and collapse into stars. This process doesn't just create new stars, it sets the stage for the formation of massive stars, the kind that collapse into core-collapsed supernovae. These stars don't live long enough to migrate far from their birthplace, so the proximity of supernova sites to potential interaction zones strengthens the case for this scenario. Additionally, NGC 2770b may have contributed not only through gravity but also through gas accretion. Some models suggest that when a dwarf galaxy interacts with a larger spiral, it can donate part of its gas reservoir, especially if it's rich in neutral hydrogen. If NGC 2770b has been bleeding gas into its companion, that material could mix with the disk of NGC 2770, enriching it with fresh, cold hydrogen capable of fueling more star formation. This intergalactic exchange isn't just theoretical, it's been observed in other interacting pairs, such as the Magellanic Clouds and the Milky Way, where massive gas bridges stretch across the sky. There's also the matter of timescale. The supernovae in NGC 2770 didn't all happen simultaneously. Instead, they were spread over a decade, a short period on cosmic scales, but one that suggests a common origin in a single star formation wave, likely triggered 10 to 30 million years earlier. That timing aligns closely with what models predict for starburst episodes induced by galaxy interactions. The cause-and-effect relationship becomes harder to dismiss as mere coincidence. Furthermore, the types of supernovae, 3-type IB events, also fit the interaction-driven star formation hypothesis. These kinds of supernovae are most often associated with massive stars that have lost their hydrogen envelopes, which can happen through stellar winds in high metallicity environments, but also through binary mass transfer, a process more common in regions of active, recent star formation. Galaxy interactions are known to boost the formation of massive binaries, by increasing gas density and stimulating the formation of massive star clusters. NGC 2770b's role may not be limited to the past, either. If the interaction is ongoing, the effects could continue for millions of years, fueling new waves of star formation and, eventually, more supernovae. The spiral arms may see further disturbances. More gas may be funneled inward. New pockets of dense stellar nurseries may ignite, all seeded by the gravitational disruption of a companion galaxy many times smaller. Interestingly, we've seen this story before. In galaxies like NGC 4038/4039, the antennae galaxies, M51 and its companion NGC 5195, or ARP-299, interactions clearly drive spectacular surges in star formation and supernova activity. While NGC 2770's interaction with NGC 2770b is less violent, it's possible that smaller-scale encounters can lead to more localized, but still significant, bursts of massive star formation. If anything, NGC 2770 may represent a more subtle case of how interactions shape galactic evolution. Rather than tearing the galaxy apart, Its companion is acting more like a whisper than a shout, a gravitational nudge that echoes through the gas clouds and leaves its mark in the form of stellar death. So while we can't definitively prove that NGC 2770b caused NGC 2770's supernova streak, the circumstantial evidence is mounting. The positioning of the supernovae, the regions of enhanced star formation, the timing of stellar evolution, and the morphology of the spiral arms all point to an ongoing relationship, one that just may have tipped the balance from ordinary star formation to extraordinary stellar death. In the vast, slow dynamics of galaxies, it's often the smallest players that make the biggest impacts. And NGC 2770b, quiet and faint though it may be, may have been the unseen hand behind one of the most intriguing supernova runs ever recorded. In cosmic terms, it may have stirred the pot just enough to light the match, and turn NGC 2770 into the galaxy that wouldn't stop exploding. With 3 dramatic supernovae already erupting in just a single decade, NGC 2770 has earned its reputation as a Supernova Factory. But now that the dust of SN1909, SN2007 and SN2008D has settled into the galaxy's archives of stellar memory, the question naturally arises, could there be more to come? Is NGC 2770 done with its fireworks? Or is it merely pausing, taking a breath before the next burst of stellar death lights up its spiral arms once again? The answer lies not in guessing, but in a careful reading of stellar life cycles and galactic rhythms. To estimate whether NGC 2770 might produce more supernovae in the near future, astronomers analyzed the same principles that predicted the last ones: star formation history, massive star populations, and galactic environment. And by those metrics, there's every reason to believe that the show is far from over. Let's begin with the raw material: massive stars, those weighing at least 8 times the mass of our Sun. These are the cosmic heavyweights destined to end their lives in spectacular collapses, giving rise to Type II, IB, or IC supernovae. When such a star is born, it races through its nuclear fuel, living fast and dying young, typically within 3 to 30 million years. That means that if a burst of star formation occurred in NGC 2770 around 20 million years ago, many of those stars may still be alive today, but not for much longer. Some could be teetering right on the edge of collapse at this very moment. Astronomers suspect that the 3 known supernovae from 1999 to 2008 likely came from a common generation of stars formed in a prior burst, possibly triggered by gravitational interaction with NGC 2770b. If that star-forming event was strong enough, it may have seeded the galaxy with hundreds or even thousands of massive stars, some of which have already died, but others which are still ticking toward detonation. Given this, the idea that NGC 2770 may produce more supernovae soon isn't far-fetched. It's quite plausible. In fact, if we apply supernova rate modeling to NGC 2770, using its star formation rate and stellar population estimates, it could reasonably be expected to produce another core collapse supernova every 10 to 30 years. That may not sound dramatic, but in astronomical terms, it's very active. For comparison, the Milky Way, much larger and more massive, only produces a visible supernova roughly once every 50 to 100 years, and even those are often hidden behind dust. But beyond statistical forecasting, there's now an infrastructure of real-time monitoring in place. Ever since the accidental discovery of SN2008D's shock breakout, NGC 2770 has earned a place on the watch lists of several global observatories and survey programs. Projects like the Zwicky Transient Facility, ZTF, and the upcoming Vera Rubin Observatory are constantly scanning the sky for sudden changes in brightness, transients that could signal the birth of a new supernova. Because NGC 2770 is a known supernova hotspot, it receives special attention. There are already archives of pre-imaging data that allow astronomers to compare changes in brightness frame by frame, increasing the odds of detecting a new event not days or hours after it happens, but potentially minutes. And if another supernova does erupt in NGC 2770, astronomers now have the tools and playbooks to respond instantly. Multi-wavelength telescopes would spring into action, measuring the X-ray, ultraviolet, optical, infrared, and radio emission from the very start. Instruments aboard satellites like Swift, NICER, or Rosetta could potentially catch another shock breakout, or even more exotic early behavior, perhaps a precursor outburst, or the emergence of relativistic jets. There's also a real hope that a future supernova in NGC 2770 could provide even more detailed data than SN2008D. New instruments, more sensitive detectors, and machine learning-assisted alert systems are in place now, tools that simply didn't exist during the last explosive event. We are better equipped, both technologically and conceptually, to capture and interpret a stellar death from the very first photon to the final fading glow. But perhaps the most tantalizing reason to keep an eye on NGC 2770 isn't just the potential for another supernova, but for a supernova that breaks the mold. While SN2008D gave us the first shock breakout in X-rays, the next event could be something else entirely. A type ICPL, broad-lined, a magnetar-powered supernova, or even one accompanied by a low-luminosity gamma-ray burst. Given the galaxy's apparent tendency to produce stripped-envelope supernovae, the odds of catching an exotic or rare variant are better here than in most galaxies. Then there's the question of whether NGC 2770 is still actively forming massive stars. Star formation can occur in waves, often stimulated by prior explosions. The energy and shock waves from past supernovae, like those already recorded, can compress nearby gas clouds, creating the conditions for the next generation of stars. This self-propagating process, known as positive feedback, suggests that the very supernovae that made NGC 2770 famous may be planting the seeds for future ones. In this way, the galaxy becomes not just a supernova factory, but a self-sustaining one. The spiral structure of NGC 2770 also helps the cycle persist. Spiral arms naturally act as compression zones where gas clouds pile up and form stars. As long as gas remains in the disk, and no catastrophic event depletes it, the galaxy can continue to birth massive stars, and eventually, watch them die in luminous blasts. And what of the companion, NGC 2770b? If the interaction is still ongoing or if there are future passes to come, additional tidal disturbances could ignite new regions of star formation. The gravitational interaction between the two galaxies may still be playing out on a timescale of hundreds of millions of years, meaning new waves of activity could yet unfold. It's possible that the most spectacular events from this galactic pairing are still ahead. In the end, predicting supernovae is a lot like trying to forecast earthquakes. We know the conditions, we understand the pressure points, we can identify fault lines, but the exact moment of eruption remains elusive. And yet, in NGC 2770, all the signs point to the potential for more stellar deaths in the foreseeable future. It's a ticking stellar clock, and astronomers around the world are listening carefully for its next chime. So when will the next explosion happen? In a year? A decade? No one knows for certain. But if history is any guide, and in the cosmos, history tends to rhyme, then NGC 2770 still has stories to tell. And one night, with no warning, it may again light up the darkness with the final scream of a massive star dying far from home, but right on schedule. NGC 2770 may have captured the astronomical world's attention with its trio of type IB Supernovi, but it's far from alone in its role as a prolific graveyard for massive stars. Across the universe, a handful of galaxies stand out as true supernova factories, cosmic environments where the life cycle of massive stars is compressed and accelerated, and where stellar death becomes a routine part of the galactic rhythm. To fully appreciate NGC 2770's place in this volatile pantheon, it's essential to compare it with other galaxies that have earned similar reputations. Galaxies like ARP 299, M82, and a few select others not only match NGC 2770's output, but in some ways, far exceed it. Let's begin with one of the most well-studied and explosively active galaxies in the sky, ARP 299. Located around 140 million light-years away in the constellation Ursa Major, ARP 299 is a chaotic merger of two galaxies, NGC 3690 and IC 694. This galactic train wreck has produced at least 7 recorded supernovae in the past few decades, with several likely missed due to heavy dust obscuration. What sets ARP-299 apart is its ferocious starburst activity, a result of tidal forces between the merging galaxies compressing vast clouds of gas and triggering rapid star formation. These intense conditions have given birth to massive stellar populations with lifespans measured in millions of years, which is to say, short, fast, and extremely explosive. The difference in environment is striking. ARP-299 is essentially a supernova furnace, constantly fueled by the gravitational energy of a merger. Its dust-rich regions hide the formation and death of stars from visible light, but infrared and radio telescopes pierce the smoke to reveal a relentless pace of stellar destruction. In contrast, NGC 2770's spiral disk remains relatively orderly, lacking the extreme violence of a merger. Its supernovae appear not to be the result of explosive interaction, but of sustained, moderate star formation that is unusually efficient at producing stripped envelope progenitors. Another benchmark galaxy is M82, the so-called cigar galaxy, lying about 12 million light-years away in Ursa Major. M82 is a starburst galaxy par excellence. Its central regions churn out new stars at rates 10 times that of the Milky Way, a frenzy of creation driven largely by gravitational interaction with its larger neighbor, M81. This sustained disturbance has given rise to a high density of superstar clusters, many of which are filled with young, hot, massive stars, the raw material for a supernova storm. Over the years, M82 has produced several supernovae, including the highly notable SN2008D, a Type I event that became one of the nearest and brightest supernovae observed in recent decades. While Type I explosions come from white dwarfs rather than massive stars, M82's overall population of short-lived giants means it likely has a significant unobserved rate of core collapse supernovae, especially hidden behind its dense veils of dust. In fact, radio surveys suggest that dozens of supernova remnants are scattered throughout its central regions, evidence of a violent recent past. Compared to M82, NGC 2770 is quieter, colder, and more conservative in its star-forming behavior. And yet, paradoxically, it has yielded more directly observed core collapse events in a shorter span of time. Why? Because M82's supernovae are largely shrouded, while NGC 2770, thanks to its lower dust content and orientation, offers a clearer line of sight. This means that while M82 may produce more supernovae, NGC 2770 may be better positioned for astronomers to actually witness them. Moving to another example, NGC 6946, often dubbed the Fireworks Galaxy, is perhaps the most iconic of all known supernova factories. Positioned just 25 million light-years away between the constellations Cepheus and Cygnus, NGC 6946 has unleashed at least 10 supernovae in the past century, a staggering figure by galactic standards. This is largely due to its elevated star formation rate, its rich molecular gas reserves, and its well-developed spiral arms, all of which are efficient environments for birthing massive stars. However, even NGC 6946 seems to differ from NGC 2770 in terms of supernova diversity. The Fireworks Galaxy has produced a wide range of explosion types, Type II, Type IB, and even a few unclassified ones, reflecting a broad range of progenitor masses and conditions. NGC 2770, by contrast, has exhibited a curious bias toward Type IB events, suggesting a specific kind of star formation environment or stellar population. This consistency makes it an especially valuable case study for that specific supernova subtype. Then there are rarer cases like NGC 1316, a galaxy in Fornax that, while less prolific overall, has hosted several bright supernovae, including multiple Type I events. Or NGC 5253, a dwarf starburst galaxy that may be on the verge of becoming a future supernova factory as it forms dense clusters of massive, luminous stars within its compact core. What unites all of these galaxies, whether they are spirals, dwarfs, or mergers, is a common set of ingredients: gas-rich environments, active or recent star formation, and often external gravitational influence. These galaxies are not static star cities. They are dynamic, churning ecosystems where massive stars rise and fall in cosmic timescales so short that, for a few rare decades, we on Earth can watch their deaths unfold. What makes NGC 2070 so fascinating in this context is that it defies the stereotype. It doesn't look like a supernova factory. It doesn't have the chaos of ARP 299, the blazing core of M82, or the high-end spiral symmetry of NGC 6946. It's a modest, dusty spiral sitting quietly 88 million light-years away, without the visual clues that scream explosive activity. And yet, it's punched above its weight, delivering 3 stripped envelope core collapse supernovae with the kind of precision that astrophysicists can't help but pay attention to. It's a reminder that supernova factories don't always wear the badge on their sleeve. Some are loud and blazing. Others, like NGC 2770, whisper their violence from a distance. But they all share a commitment, dictated by the physics of star formation and stellar death, to enriching the universe with heavy elements, to shaping the interstellar medium, and to leaving behind the remnants, black holes, neutron stars, and hot glowing nebulae, that tell the story of their dead stars. In the grand galactic registry of violent star death, NGC 2770 holds a unique page. Not the brightest, not the noisiest, but perhaps the most surprisingly instructive. A galaxy whose calm facade belies a history written in detonations. It joins the ranks of ARP 299 and M82, not by shouting, but by catching our attention when we least expected it. A quiet factory, yes, but one whose output continues to shape the future of supernova science. In the vast tapestry of the cosmos, not all galaxies are created equally when it comes to birthing and burying stars. Some galaxies slumber, cradling older, low-mass stars in peaceful spirals with little drama. Others burn with an intensity that defies their size, throwing massive stars into existence, only to watch them collapse within a cosmic blink. To understand why galaxies like NGC 2770, and others like ARP 299 and M82, earn the title of supernova factories, we must first dive into the intricate recipe that makes a galaxy truly explosive. The central ingredient in this volatile cocktail is massive stars. These titans, typically more than 8 times the mass of our Sun, are the only ones capable of ending their lives in core collapse supernovae. Their size grants them intense gravitational pressure, which fuels a rapid cycle of nuclear fusion. But this comes at a cost. These stars burn hot and fast, depleting their fuel in mere millions of years, and when that fuel runs out, gravity wins, crushing the core and triggering an explosion of almost unimaginable force. But massive stars don't arise randomly. They are born from dense molecular clouds, the coldest, darkest, and most fertile regions in a galaxy. These clouds, sometimes stretching hundreds of light-years across, contain the raw material, hydrogen gas. Under the right conditions, gravity causes these clouds to collapse, fragment, and form stars. The more massive the cloud, the more massive the stars that can form within it. And here's the key. The rate at which a galaxy forms massive stars is the primary driver of its supernova rate. This brings us to the next major ingredient, active star formation. Galaxies with high star formation rates, those that are constantly converting gas into new stars, are the ones that keep fueling the fire. It's not just about quantity, though. It's about efficiency. Some galaxies can form thousands of stars per year, but if most of those are low-mass red dwarfs, they won't contribute to the supernova count for billions of years, if at all. What makes a galaxy explosive is a bias toward high-mass star formation, often tied to environmental factors like gas density, turbulence, and metallicity. Starburst galaxies like M82 and ARP 299 are excellent examples. These galaxies aren't just forming stars, they're doing so at an accelerated rate, often due to gravitational interactions or mergers. These cosmic collisions stir up the galactic disk, compress gas clouds, and trigger massive waves of star birth. The result is a boom of massive stars, and within a few million years, a boom of supernovae. ARP 299, for instance, is estimated to produce one supernova every few years, a rate orders of magnitude above that of the Milky Way. But explosions don't always need chaos. Even a relatively calm galaxy like NGC 2770 can produce multiple supernovae if the conditions are just right. That's where metallicity enters the equation, the proportion of elements heavier than hydrogen and helium in the gas clouds. Higher metallicity leads to stronger stellar winds, which can strip away a star's outer hydrogen layers, creating the kind of stripped envelope progenitors seen in type IB and IC supernovae. In lower metallicity environments, massive stars might retain more of their hydrogen and explode as type II instead. Metallicity also influences the cooling efficiency of gas, affecting how easily clouds collapse into stars. Galaxies with moderate metallicity, like NGC 2770, may strike a balance that allows for both the efficient formation of massive stars and the loss of their hydrogen envelopes, making them fertile grounds for type IB supernovae, specifically. Another critical factor is stellar population age. For a galaxy to have frequent supernovae now, it must have formed a large number of massive stars 10 to 40 million years ago. That time window is the sweet spot, the interval between birth and death for stars of different masses. Galaxies with recent starbursts will enter this phase of frequent supernovae a few million years later, and the echo of those starbursts will ring out as a cluster of supernova explosions, one after another, across a span of decades. This leads naturally to another factor: clustering of massive stars. Supernovae are not evenly distributed across a galaxy. They often emerge from stellar associations and massive star clusters, where dozens or hundreds of massive stars are born together. These clusters act like ticking time bombs. Their massive members die off in succession, each triggering shockwaves and potential new star formation in nearby gas. Galaxies rich in such clusters, especially those located in spiral arms or near galactic centers, are ripe for explosive events. Then there's the matter of galactic dynamics. Spiral arms, for instance, are not static structures but rather density waves that sweep through the disk. These waves compress gas as they pass, leading to star formation, particularly of massive stars. That's why many supernovae, including those in NGC 2770, are found near or within spiral arms. The dynamic structure of a galaxy determines where and how often gas gets compressed into stars. Additionally, galaxy interactions and mergers remain among the most powerful triggers of explosive activity. When a dwarf galaxy brushes past a spiral, or when two large galaxies collide, the gravitational chaos can funnel gas toward the center, create tidal tails, or compress gas clouds in the disk. These interactions can sustain decades or even centuries of heightened star formation, and therefore an elevated risk of supernovae, long after the first encounter. There's also the more nuanced role of binary star systems. Many of the supernovae observed, especially stripped envelope types, are now believed to come from stars in close binaries. In such systems, one star can strip material from its companion, altering its evolution and leading to a premature supernova. Galaxies with high binary fractions, especially tight binaries, may produce more type IB and IC supernovae, even without especially high overall star formation rates. This may be part of the explanation for NGC 2770's supernovae being consistently type IB, hinting at a binarity-rich stellar population. Finally, galactic orientation and dust content affect our ability to observe these events. A galaxy might be just as explosive as NGC 2770 but oriented edge-on, with a thick layer of dust hiding most of its activity. NGC 2770's favorable orientation and relatively moderate dust levels make it a perfect laboratory to observe these rare deaths unfold in real time. It may not be the most active, but it's among the most visible, which makes all the difference. To summarize, the recipe for an explosive galaxy goes like this: start with plenty of gas, stir in metallicity at just the right level, ensure a steady or triggered star formation rate, add in massive stars, ideally in clusters or binary systems, sprinkle with tidal interactions, and wait. Within a few million years, the sky will light up with the violent deaths of stars, and the galaxy will leave its mark as a supernova factory. NGC 2770 is not explosive in the way of starburst galaxies or merger remnants. Its quiet outer spiral arms conceal a delicately tuned environment that produces just the right conditions for core collapse supernovae, especially type IB. That balance is what makes it so compelling. It didn't need violence or chaos to become a supernova factory. It needed only the subtle alignment of galactic ingredients, quietly simmering until they reached a boiling point of stellar death. Since the remarkable sequence of type IB supernovae in NGC 2770, 3 events in just 10 years, astronomers have shifted their gaze toward this seemingly unassuming spiral galaxy with renewed determination. It's not just a place of past explosions, it's a laboratory of potential, a celestial time bomb with its fuse already lit. The triple outburst turned NGC 2770 into a prime candidate for regular observational campaigns, and today it stands among a handful of galaxies monitored systematically for the sudden flicker of another dying star. After SN2008D's unprecedented detection via X-rays, something changed. That event didn't just give us a supernova, it gave us a new paradigm. Astronomers realized that if such an explosion could be caught in the very act of going off, other galaxies like NGC 2770 might be capable of offering up similar real-time phenomena. Since then, the community has moved from passive observation to proactive surveillance, creating a web of observatories, both on Earth and in orbit, poised to react at the faintest whisper of another detonation. At the heart of these efforts are the automated transient surveys, wide-field sky cameras that scan the heavens night after night, looking for objects that change brightness unexpectedly. Among them is the Zwicky Transient Facility ZTF, operating from Palomar Observatory in California. ZTF covers the entire northern sky every few nights and is particularly adept at detecting sudden outbursts, like those from supernovae in nearby galaxies. NGC 2770, with its relatively bright and clean profile, is a regular target in these sweeps. ZTF isn't alone. It's joined by the All-Sky Automated Survey for Supernovae, ASUS-SN, a global network of small telescopes that monitors the entire sky to magnitude 17. Its goal is simple: catch supernovae early and alert the world. NGC 2770 sits comfortably within ASUS-SN's range, and the galaxy is routinely flagged for comparison during nightly data processing. Beyond these automated surveys, professional observatories with dedicated time for transient follow-up, like Keck, Gemini North, Subaru, and Very Large Telescope, VLT, are primed to spring into action when a signal from NGC 2770 pops up. These powerful instruments are capable of dissecting a supernova's light into spectra, revealing the chemical fingerprints of the explosion, measuring the velocity of ejected material, and providing insights into the nature of the progenitor star. Since NGC 2770 has already yielded such valuable results, time on these telescopes is often pre-approved for follow-up in the event of another event there. On the space-based side, NASA's Neil Gehrels Swift Observatory, which famously captured the X-ray flash of SN2008D, continues to monitor known galaxies with supernova potential. Swift is a rapid-response observatory. When alerted by a ground-based trigger, it can pivot to the source and collect data in X-ray, ultraviolet, and optical wavelengths. While it isn't watching NGC 2770 continuously, it remains on call, and if another burst were detected, Swift would almost certainly be among the first instruments to respond. Soon, the observational power will grow exponentially with the full deployment of the Vera C. Rubin Observatory in Chile. With its large synoptic survey telescope, LSST, Rubin will scan the entire southern sky every few days to unprecedented depth. Although NGC 2770 is in the northern sky and thus outside Rubin's direct purview, the Rubin model is inspiring similar capabilities in upcoming northern projects. The technology and cadence developed for Rubin will inform next-generation monitoring systems that will further intensify coverage of galaxies like NGC 2770. Meanwhile, amateur astronomers and citizen science platforms like Galaxy Zoo and Supernova Hunters have become critical players in the game. With better access to data than ever before, skilled amateurs regularly analyze survey data, comparing frames for signs of new transients. NGC 2770's name now carries a kind of informal watch list status. It shows up in forum posts, in amateur catalogs, and in nightly logs of observers scanning the Virgo and Lynx regions. Given its prior behavior, many eyes, professional and civilian alike, remain fixed upon it. More advanced tools are also on the horizon. Instruments like JWST and Euclid, though not primarily designed for transient hunting, could be used in follow-up once a new supernova is detected. Their sensitivity in the infrared will allow astronomers to peer deeper into dust-shrouded regions, revealing the heart of the explosion even if it's embedded in dense interstellar clouds. But perhaps the most forward-looking development is the integration of AI-driven early warning systems. Machine learning models trained on thousands of supernova light curves can now flag early-stage events long before human observers would have noticed them. These systems are being tied into telescope scheduling networks, meaning that NGC 2770 could be automatically targeted within minutes of a detected anomaly, creating an automated chain from discovery to observation to publication. And there's an emotional element to these campaigns too, a sense of suspense and anticipation. Every night, astronomers know that they could be catching the next great event. Every pixel of data captured from NGC 2770 is examined with the knowledge that the galaxy could light up again at any moment. Every quiet day feels like the calm before another eruption. When SN2008D happened, it wasn't expected, it was caught by sheer serendipity. The lesson was clear: expect the unexpected, and keep watching. These observational campaigns also serve a larger scientific mission. Repeated observation of one galaxy over years or decades allows researchers to build detailed models of its stellar population, track stellar evolution in real time, and watch how interstellar material responds to past explosions. It's not just about catching supernovae, but about understanding the life of the galaxy as a whole, how it digests the aftermath of explosions, how it refuels star formation, and how it prepares for the next round. In this way, NGC 2770 has become a kind of cosmic stage, and telescopes around the world are its dedicated audience. The curtains may be drawn at the moment, but the lights are on, the observers are watching, and everyone is waiting for the next act. Now imagine, for a moment, that NGC 2770 wasn't sitting 88 million light-years away in the Constellation Lynx, comfortably distant and safely isolated. Imagine instead that it was right next door, within the same galactic neighborhood as the Milky Way, or even worse, that our galaxy shared the same explosive nature. What if the Milky Way itself was a supernova factory, erupting with massive stellar deaths every few years? What would that mean for our planet, our solar system, and life as we know it? The consequences would ripple far beyond a few pretty lights in the night sky. Supernovae are not just luminous events, they're astrophysical forces of destruction and creation, hurling out deadly radiation, high-energy particles, and shockwaves powerful enough to shred nearby star systems. If the Milky Way erupted in a similar fashion to NGC 2770, say, 3 core collapsed supernovae in a decade, the effects on our cosmic environment would be anything but benign. To understand the potential impact, we have to start with the lethal zone of a supernova. A type IB supernova can release a flood of X-rays and gamma rays powerful enough to strip away planetary atmospheres, especially if the event occurs within about 30 to 50 light-years of Earth. That's our danger radius. A supernova at that distance or closer could deplete the ozone layer, allowing ultraviolet radiation from the sun to flood the surface of our planet. Over time, this could cause massive ecological damage, possibly even contributing to mass extinction events. And this isn't just theoretical. Some scientists believe that a supernova or gamma ray burst may have played a role in the Ordovician-Silurian extinction about 450 million years ago, when roughly 85% of marine species disappeared. While no nearby supernova remnants have been conclusively tied to that event, the possibility remains chillingly plausible. If our galaxy were to produce supernovae at NGC 2770's rate, the odds of having such an event occur within the danger radius would rise dramatically. Even supernovae farther away, say, within a few hundred light-years, could still have consequences. The Earth would be bombarded with cosmic rays, high-energy particles capable of penetrating the atmosphere and potentially altering the planet's climate. Cosmic rays can also interact with nitrogen and oxygen in the upper atmosphere to create nitrogen oxides, which could further erode the ozone layer. On a human scale, these rays can be dangerous to astronauts and could degrade satellites or electronics in space. Now consider a scenario where a star as close as Betelgeuse, a red supergiant just 642 light-years away, goes supernova. While that's outside the kill radius, it would still be one of the brightest objects in the sky, visible during the day for weeks or months. It would cast shadows at night and possibly affect Earth's ionosphere. A supernova within that range wouldn't be apocalyptic, but it would definitely disrupt our cosmic peace. If the Milky Way was producing supernovae every few years, and some of them occurred within a few hundred light-years of us, the long-term impacts could accumulate. Even if each event wasn't individually catastrophic, their cumulative radiation effects, cosmic ray exposure, and disruptions to our magnetic field could shape the evolution of Earth's biosphere over millennia. But it's not all doom. Supernovae also enrich the galaxy, and if the Milky Way behaved like NGC 2770, it would be a crucible of stellar transformation. These explosions seed the interstellar medium with heavy elements, carbon, oxygen, iron, gold, the very building blocks of planets, life, and technology. Our solar system itself formed from the ashes of ancient supernovae, mixed into a cold cloud that eventually collapsed to form the Sun and its surrounding planets. Without supernovae, Earth wouldn't have iron in its core, oxygen in its air, or calcium in its bones. A Milky Way filled with frequent supernovae would likely be a more metal-rich galaxy, which could mean more terrestrial planets, more potential biospheres, and faster chemical evolution in star-forming regions. It's possible that in such a galaxy, life would evolve faster, or it might never get the chance, as each promising start gets reset by waves of radiation and instability. There's also the human fascination with the night sky. If supernovae were a regular part of our sky, if every few years a new star burst into brilliance, outshining everything around it, our relationship with the universe would be very different. Astronomers would benefit immensely. With regular supernovae so close by, the science of stellar death would become an observational science, not just a statistical or archival one. We could study shock breakouts in exquisite detail, resolve the remnants as they evolve, and perhaps even watch neutron stars form and cool in real time. The data would flow like a river. Telescopes would remain trained on recent remnants as a matter of routine. But it would also change how we think about safety in space. We would need more robust protection for satellites and astronauts. Missions beyond Earth's magnetic shield would face higher risks. Human colonization of the Moon or Mars would require radiation-hardened habitats. Spacefaring civilizations might have to develop early warning systems for nearby stellar collapse, just as we track asteroids today. In short, if the Milky Way had the same explosive personality as NGC 2770, Earth would be a planet of heightened astronomical vigilance. Our biosphere, our technologies, and our imaginations would all be shaped by the looming reality that the stars around us are not stable points of light, but unstable fuses, ready to detonate at the end of their brief, luminous lives. We'd live with the knowledge that somewhere in the spiral arms, a star might be dying, now, tonight, or tomorrow, and its final message would be a wave of radiation, a burst of particles, and a story told in light across the sky. Perhaps that thought alone explains why NGC 2770 so captures our interest. Supernovae, despite their violent finales, are among the most generous processes in the cosmos. When a massive star reaches the end of its life and erupts in a spectacular death throe, it doesn't merely vanish into darkness. Instead, it spills its insides across the galaxy, gifting the interstellar medium with the very ingredients that make planets, life, and future stars possible. In a universe driven by cycles, supernovae are the ultimate agents of cosmic recycling, turning destruction into renewal. In the heart of every massive star, elements are forged through the relentless process of nuclear fusion. It starts with hydrogen, fusing into helium, and continues step by step up the periodic table: carbon, oxygen, neon, magnesium, silicon, and finally iron. But when the core of a massive star becomes iron, the game changes. Iron cannot produce energy through fusion, it costs energy instead. And when fusion stops, the core collapses, gravity takes over, and the supernova begins. What happens next is one of the most extreme events in the universe. The outer layers of the star rebound off the collapsing core and explode outward at thousands of kilometers per second, carrying with them the ashes of millions of years of fusion. But this explosion does more than eject what the star already had. It creates new elements in the process. Through a process known as nucleosynthesis, the extreme heat and pressure of the supernova itself forge heavier elements, those beyond iron, like cobalt, nickel, copper, silver, gold, lead, and uranium. These elements, rare and precious, don't come from peaceful stars. They are born in the fire of stellar death. Every atom of gold in a wedding ring, every atom of iodine in your thyroid, every atom of calcium in your bones was created in a supernova. Or, in some cases, in even more exotic explosions like neutron star mergers. Without supernovae, the periodic table would be a pale shadow of itself. Life, at least life as we know it, would be chemically impossible. Once ejected, this material doesn't drift aimlessly. It becomes part of the interstellar medium, mixing with the cold clouds of gas and dust that weave through the galaxy. Over time, gravity draws these enriched clouds back together. Dense regions collapse, forming new stars. And with them come new planetary systems, now seeded with the heavy elements forged in past generations of stars. This is how galaxies evolve, not only through star formation, but through star death and rebirth, each cycle adding new complexity to the fabric of cosmic chemistry. This is especially evident when comparing older galaxies to younger ones. Early galaxies, formed shortly after the Big Bang, were composed almost entirely of hydrogen and helium, the lightest elements. Their stars were massive, hot, and short-lived, and their deaths were the first great explosions to enrich the universe. Over billions of years, with each generation of stars, galaxies have become more metal-rich, a term astronomers use to describe the abundance of elements heavier than helium. Our own Milky Way is now home to countless metal-rich stars, planets, and living things, all thanks to these cycles of supernovae. NGC 2770, with its string of type IB Supernovi, is an active participant in this galactic recycling process. Each supernova it has produced has injected new material into its spiral arms, oxygen, silicon, iron, and more, blending into the interstellar clouds that may eventually birth new stars. And because type IB supernovae come from massive stars that have lost their hydrogen envelopes, they may enrich the surrounding medium with elements typically deeper in the stellar core. This elemental diversity affects what kinds of stars and planets will form next. These explosions also energize their surroundings in other ways. The supernova shockwave, a tsunami of high-speed gas, plows into the surrounding medium, compressing it. This compression can cause nearby gas clouds to collapse, triggering new rounds of star formation. In this way, supernovae act not only as destroyers but also as catalysts. The death of one star can spark the birth of many more. It's a beautiful, interconnected cycle. A supernova goes off. Its remnants spread across the galaxy, enriching and stirring the interstellar medium. New stars form, born of old material. Some of them are massive enough to go supernova in turn, starting the process all over again. With each loop, the galaxy becomes more chemically complex, more dynamic, and more capable of supporting planets, moons, atmospheres, and perhaps life. This is why astronomers say that we are made of star stuff. It's not just poetic, it's literal. The carbon in your DNA, the oxygen you breathe, the iron in your blood, all of it was once part of a star that ended in a supernova. Without these explosions, the universe would be sterile, dominated by hydrogen and helium, devoid of the chemistry required for biology, geology, and technology. Supernovae also leave behind legacies in the form of supernova remnants, expanding clouds of energized gas and dust. These remnants glow for thousands of years in X-ray, radio, and optical wavelengths. Famous examples like the Crab Nebula, the remnant of a supernova observed in 1054 AD, and Cassiopeia show us the anatomy of past explosions and help us understand how their energy shapes the galactic environment long after the flash fades. In NGC 2770, the remnants of SN1999E, SN2008Y, and SN2008D are likely still expanding today, invisible to most amateur telescopes but glowing in wavelengths we can capture with powerful instruments. These remnants are repositories of information, containing clues about the composition of the star, the dynamics of the explosion, and the nature of the surrounding gas. In future decades, the remnants of these explosions may cool and settle into the galaxy's structure, eventually becoming part of a molecular cloud, and then, in millions of years, part of a new star. Perhaps one day, far in the future, a civilization in NGC 2770 will find themselves on a planet whose crust is enriched with elements from these very supernovae, unaware that their world was made possible by a violent event that we, here on Earth, observed in 2008. That is the legacy of supernovae: death giving way to life, chaos seeding structure, destruction laying the foundation for creation. In this way, galaxies are not static islands of stars, they are living systems, built on cycles of birth, growth, collapse, and renewal. And supernovae, with all their fury and brilliance, are the pulse that keeps it all moving. Given how vast and complex the universe is, it's almost certain that NGC 2770 isn't alone. In fact, it may not even be exceptional, just one of the few supernova factories we've actually caught in the act. The cosmos is a dark and often deceptive place, and our instruments, as advanced as they are, only see a small slice of the whole picture. This leads to a tantalizing question: how many other galaxies like NGC 2770 are out there, producing supernovae in rapid succession, completely unnoticed? The answer begins with the limitations of our current observational reach. Most transient surveys, even the most advanced like CTF and OSIS-SN, are bound by constraints in sensitivity, cadence, field of view, and atmospheric clarity. Galaxies on the far side of the Milky Way are hidden behind dense clouds of interstellar dust that absorb visible light. In other cases, edge-on galaxies, where the thick galactic plane blocks our view of the star-forming regions, may be hiding multiple supernovae that either never reach us or are too dim or redshifted to recognize for what they are. Distance is another major factor. NGC 2770 is about 88 million light-years away far, but still within what astronomers call the nearby universe. We can study it in detail, resolve its spiral arms, and follow its individual supernovae. But go just a few hundred million light-years further, and suddenly it becomes much harder to detect type IB or type IC supernovae unless they are particularly bright. The farther away the galaxy, the more difficult it becomes to monitor subtle or rapidly fading transients. It's entirely plausible that there are hundreds or thousands of NGC 2770-like galaxies at greater distances, producing clusters of supernovae that go largely unrecorded. Then there's the issue of observational bias. Historically, supernova searches were focused on bright, nearby, well-known galaxies, especially those rich in star formation. Many spiral galaxies in quiet regions of space were overlooked simply because they weren't on target lists. Even now, some transient surveys focus on high-probability regions, unintentionally skipping over obscure, dusty, or edge-on galaxies. As a result, a supernova in a faint or oddly shaped galaxy might be missed altogether or misclassified as noise. Some galaxies might even be producing supernovae deep within their dusty cores, where the optical light of the explosion is smothered by interstellar material before it can escape. These so-called dark supernovae wouldn't show up in visible wavelengths at all, but might glow faintly in infrared or X-ray. Without specialized instruments like the James Webb Space Telescope or Chandra X-ray Observatory, these events remain completely invisible to ground-based surveys. That means entire populations of explosive galaxies could be hiding in plain sight, shrouded by their own internal clouds, like embers glowing within a bank of fog. There's also the possibility that some galaxies go through temporary phases of elevated supernova activity. Just like starburst galaxies that flare up after a merger or interaction, it's conceivable that a quiet spiral could undergo a burst of massive star formation, due to gas accretion, bar instabilities, or shockwaves passing through, leading to a brief epoch of prolific stellar death. If that phase lasts only a few million years, it might come and go before our instruments ever catch on. NGC 2770 may simply be in one of these transitional phases, giving us a rare glimpse into something more common but fleeting. In fact, looking at galaxies like ARP 299 and M82, which have had multiple observed supernovae, we start to see patterns. Both are undergoing intense star formation, driven by mergers or strong gravitational interactions. Their central regions are dust-choked and turbulent, yet they continue to produce stellar explosions at rates far higher than average. These galaxies are considered archetypes of high supernova rates, but even they might be undercounted. The true number of supernovae occurring within them could be higher. It's just that we miss the fainter ones, the ones that don't break through the dust, or the ones that happen during daytime on Earth when no telescope is watching. Moreover, galaxies in the early universe, when star formation rates were significantly higher, must have produced supernovae at astonishing frequencies. We know from surveys like those from the Hubble Space Telescope and JWST that galaxies at high redshifts were forming stars at blistering paces, often 10 or even 100 times faster than the Milky Way does today. That means these ancient galaxies were likely true supernova factories, with massive stars living and dying in rapid succession, shaping the evolution of the young cosmos. But even in our own galactic neighborhood, there's strong evidence suggesting we're missing some events. Studies of isotopic anomalies in deep-sea sediments on Earth, such as the discovery of iron-60, have hinted at the presence of supernovae occurring within 100 light-years in the last few million years, without any known historical record of such explosions. That tells us that some supernovae happen undetected, even in our own backyard. And what about entire dwarf galaxies, faint and difficult to detect? Some of them may have very high specific star formation rates, meaning they form more stars relative to their mass. If one of these low-mass galaxies suddenly begins producing massive stars in a cluster, it could unleash several core-collapse supernovae in quick succession, and we'd never know unless it was caught in a transient survey by chance. As new instruments come online, the number of detected supernovae is increasing rapidly. Yet each new detection reminds us that there's far more still hidden, behind dust, distance, or time. We've only scratched the surface of the supernova population. As machine learning, infrared surveys, ultra-wide field telescopes, and X-ray satellites become more advanced and coordinated, we'll begin to uncover more of these factories, one unexpected burst at a time. Ultimately, NGC 2770 may be less an anomaly and more a signpost, pointing toward a larger, hidden population of galaxies that live fast and die bright. If we've learned anything from studying it, it's that the cosmos is always more dynamic than it appears. The still, silent night sky hides a relentless churn of creation and destruction, and if we keep watching long enough, we might discover that the universe is littered with factories, each one quietly forging the elements of everything that was, is, and will be. NGC 2770's place in astronomical history isn't secured by grandeur, size, or proximity. It earned its legacy by transforming how we observe death itself. Before this quiet spiral galaxy lit up with 3 type IB Supernovi in just 10 years, astronomers had caught supernovae often, but rarely with such timing, clarity, and evolutionary insight. In many ways, NGC 2770 became the first real-time supernova laboratory, showing the astrophysical community not just how to react to these events, but how to anticipate, monitor, and learn from them while they're still unfolding. Its most profound impact began with SN2008D, the first supernova ever caught during its X-ray shock breakout phase, an astonishing moment where astronomers witnessed the birth cry of a dying star. That chance detection by the Swift satellite while observing another supernova was, at the time, entirely unplanned. But the implications were immense. It meant that with the right instrumentation, we could observe supernovae not just days after they exploded, but seconds after they began. It opened up the possibility of real-time supernova astronomy, seeing not just the glowing embers, but the flash that starts the fire. Before this, supernova research was largely retrospective. Astronomers would notice a brightening star days or even weeks after the explosion and then work backward using spectral data and light curves to reconstruct what had happened. NGC 2770 changed that paradigm. SN2008D's early light, captured in X-rays and quickly followed by ultraviolet and optical data, gave scientists a complete timeline, from the initial shock breakout to the cooling envelope and late-time radioactive decay phases. It was a near-perfect sequence. This changed how telescopes were tasked. Observatories around the world began integrating target of opportunity protocols, where a sudden alert, like an X-ray flash or a transient brightening, could cause telescopes to swing immediately toward a promising source. Instead of waiting for nightly survey data to be processed, astronomers could act within minutes. SN2008D proved that the early signals were not only scientifically valuable but essential for understanding the explosion physics and the nature of the progenitor star. NGC 2770 also taught us that a single galaxy can be a wellspring of insights, not just a one-off data point. By producing 3 supernovae of the same rare type within a decade, it became a natural case study in comparative supernova research. Scientists were able to examine differences in light curves, spectral evolution, and shockwave dynamics between SN1999A, SN2007UY, and SN2008D, all in a consistent galactic environment. That removed many variables and allowed researchers to isolate the properties of the stars themselves as causes for the diversity among explosions. More subtly, NGC 2770's triple event streak refocused attention on galactic environments and how they influence stellar death. While before, the emphasis had been placed primarily on individual stars and their fates, this galaxy pushed astronomers to look outward, at the host galaxy's star formation rate, stellar population, metallicity, and even its interactions with companion galaxies. It encouraged a new branch of supernova science, not just how stars explode, but where they explode and why certain galaxies seem to nurture more deaths than others. It also emphasized the importance of multi-wavelength coordination. SN2008D was the result of one instrument seeing X-rays, which triggered ultraviolet and optical follow-ups within hours. That chain reaction proved that no single telescope, no matter how powerful, could catch the whole story. Instead, what was needed was a network, a global, collaborative observational model where radio, optical, X-ray, infrared, and even gamma-ray observatories could pool data for one event in near real time. The explosion of SN2008D gave astronomers a model for this kind of orchestration, a blueprint that would be echoed in future efforts to study kilonovae, fast radio bursts, and even gravitational wave events. And so, in this quiet corner of the sky, NGC 2770 permanently altered the methodology of supernova discovery. No longer were supernovae mere curiosities, only observable after the fact. They became predictable in context, detectable in their infancy, and vital pieces in a cosmic clockwork that could be tracked and interpreted from start to finish. It proved that our galaxy was not the only one where stellar death was both common and informative, and it suggested that there may be dozens or hundreds of such galaxies scattered across the universe, each waiting to erupt, each carrying their own stories. Perhaps the most lasting legacy of NGC 2770 is the scientific culture it inspired, one of vigilance, readiness, and rapid response. The galaxy became a symbol for why we watch the sky, not passively, but with the expectation that at any moment, something profound might unfold. It reminded us that astrophysics is not always a game of ancient echoes. Sometimes, it's a live broadcast, a light that screams across the void with a message written in radiation, magnetism, and decay. And for that reason, every time a telescope receives a supernova alert, every time a satellite shifts to focus on a rising burst of X-rays, every time a light curve begins its long, slow arc across a researcher's screen, somewhere in the methodology, the decision tree, or the instinct to move quickly, there's a piece of NGC 2770. It became not just a galaxy, but a benchmark. A pivot point. A reminder that sometimes, The most important discoveries don't come from the biggest explosions, but from the ones we catch right on time. There is something hauntingly beautiful about a galaxy like NGC 2770, a place so distant, so outwardly unremarkable, yet so filled with thunderous final acts that the universe itself seems to pause and listen. In the grand cosmic sea, where billions of galaxies drift like scattered islands of starlight, this single spiral galaxy stands apart, not by its size, or its brightness, or its proximity, but by its rhythm of rupture, its defiance of stillness. Every few years, it shatters the silence with a flash. A heartbeat of destruction. A cry of creation. NGC 2770 does not roar, it whispers in X-rays, sings in optical light, and burns with ultraviolet grief. It is a place where stars live fast and die bright, their deaths not quiet or forgotten, but transformative. Each time one of its massive suns collapses, the darkness around it is ripped apart by radiation, a brief, furious glow that tells the story of gravity's final conquest. And yet, even in that violent end, something new begins. Heavy elements are cast into the galactic winds. Gas clouds shudder. Seeds of future stars are sown. To the naked eye, NGC 2770 is a faint smudge in the Constellation Lynx. An amateur astronomer might pass over it without a second glance. It doesn't blaze like Andromeda. It doesn't sprawl like the whirlpool. It lurks in a quiet quadrant of sky, whispering its secrets only to those with patient eyes and listening instruments. But behind that veil lies a machine of cosmic evolution, a factory not of industry, but of finales and beginnings, of endings that bloom into possibility. It reminds us that the universe is not merely ancient, it is ongoing. The cosmos doesn't only echo with the light of stars long dead, it also pulses with events happening now, in real time, if only we care to look. Supernovae are not relics of a violent past. They are the present tense of creation, still unfolding, still painting the skies with ash and gold. NGC 2770 opened a door to that realization. It taught us to be vigilant, to expect the unexpected, and to understand that even the most ordinary galaxy can harbor extraordinary truths. And so we look back at this unassuming spiral with reverence. It gave us a glimpse not just of stellar death, but of a process much larger, the cycle of energy, the transfer of elements, the alchemy of time. It dared us to believe that a galaxy could be a laboratory, a witness, a storyteller. NGC 2770 didn't just produce 3 supernovae. It produced insight. It ignited a new era of observation. It reshaped how we chase light across the void. In the end, it is galaxies like this, subtle, restless, generous, that remind us why we study the stars at all. Not for trivia. Not for distance. But for what they reveal about life, death, and the rebirth written into the fabric of space itself. For in NGC 2770, we see the sky not as a quiet dome of dots, but as a living, breathing process, lit by fire, scattered by force, reformed by gravity's enduring pull. A galaxy that blew our minds not with spectacle, but with timing. Not with proximity, but with pattern. Not with myth, but with measurable truth. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.